Picture the ground beneath your feet not as solid, unchanging earth, but as a vast, silent archive. Across the globe, hidden just below the surface of deserts, jungles, and even modern cities, lie the fingerprints of lost worlds. These are not the stuff of legend, but tangible, stone-cold reality, the massive foundations of civilizations that have long since faded from memory. Entire cities, once bustling with life and ambition, have been reclaimed by the soil, their greatest achievements waiting patiently for us to listen to their stories. And what they have to tell us challenges everything we think we know about human history and our own place in it. We often gaze upon ancient ruins as beautiful, melancholy relics, but we are missing their most profound truth. They are not just piles of rock, they are masterclasses in engineering, feats of ingenuity so advanced that we are only now, with all our technology, beginning to grasp their brilliance. The real secrets aren't in the grand facades or the ornate temples, but in the very first stones that were laid, the foundations that have supported the weight of millennia. Today, we are going on a journey to uncover those secrets beneath the stones. This is an exploration of how the foundational remains of ancient cultures reveal a level of engineering mastery that rivals, and in some cases even surpasses, our modern capabilities. We will venture to sites where builders without computers or steel manipulated granite blocks with impossible precision, creating structures that have withstood earthquakes for thousands of years. We will decode the purpose of enigmatic formations that seem to defy logic and reveal how our ancestors possessed a deep, intuitive understanding of their environment, allowing them to build on swamps, carve into mountaintops, and orient their cities to the stars. This is more than an archaeological tour. It is a detective story, piecing together a forgotten science from the clues left in the bedrock. We will see how the choice of a building site, the preparation of the ground, and the laying of the first course were acts of profound intelligence, deliberate steps to create a legacy meant to last for eternity. This exploration is crucial, not just for satisfying our curiosity about the past, but for illuminating our path forward. In an age of climate change and disposable construction, the sustainable, resilient principles encoded in these ancient foundations offer us profound lessons. They teach us about building in harmony with nature, about using local materials in ingenious ways, and about planning not for decades but for centuries. By the end of our journey, you will never look at a crumbling wall or a solitary stone the same way again. You will see these places for what they truly are, vast libraries of forgotten knowledge, each block a page in a blueprint for survival and brilliance. So prepare to have your perception of history fundamentally altered. We are about to dig into the very roots of human achievement, and what we find there may just change the future. Think about the most impressive building you have ever seen. Your eyes are drawn upward to its soaring height, its elegant shape, its beautiful facade. But the true genius of that structure, the reason it can soar so elegantly, lies in the part you almost never see, the part buried in the ground. We tend to think of a foundation as just a simple, sturdy base, the unglamorous starting point of construction. But for the master builders of antiquity, it was something far more profound. It was the critical conversation between human ambition and the unyielding realities of the natural world. Every time they laid a foundation, they were engaging in a complex negotiation with gravity, which constantly tries to pull everything down, with seismic forces that can shake a city apart in moments, and with time itself, the slow, patient force of erosion and decay that grinds all things to dust. To build a foundation was to make a statement. It was a declaration of permanence, a bold claim that this creation, this city, this temple, was not just a temporary shelter but a permanent fixture on the landscape, meant to endure for generations untold. It was the ultimate expression of an empire's confidence in its own power and its technical prowess. This was not a matter of simply digging a hole and filling it with rock. The process began with a deep, almost intuitive understanding of the land itself. The choice of location was a science. Builders would assess the bedrock, test the soil's stability, and consider the flow of water through the ground. They were practicing geology and physics centuries before those words even existed. The depth of the foundation was carefully calculated too shallow, and the building would settle unevenly and crack too deep, and it was a waste of immense effort. And the materials, they weren't chosen at random. They selected stones that could bear immense weight, mixed mortars that would bind for millennia, and sometimes even engineered the earth itself to create a stable platform. This holistic view of the foundation as an integrated system is what separates ancient masterworks from mere piles of stone. It was a silent promise, a covenant made with the future, that this effort, this investment of thousands of lives would not be in vain. We are only now, with our advanced tools and sciences, beginning to fully appreciate the sophistication of that promise. And to understand how they kept it, we must first look at the very stuff they built with the mysterious materials that have defied time itself. Now, let's turn our attention from the grand philosophy of foundations to the very substance that gave them life, the materials. And there is perhaps no better place to start than with one of the most baffling mysteries in all of ancient engineering: Roman concrete. Picture the great breakwaters of the Roman harbor at Caesarea Maritima, massive structures that have been pounded by the waves of the Mediterranean Sea for over 2,000 years. While our modern concrete ports often crumble and require constant repair after just a few decades, these ancient maritime monuments are not just standing, they are incomprehensibly getting stronger. This is not the simple lime mortar you might associate with old buildings. What the Romans created was a sophisticated geopolymer, essentially an artificial rock, born from a chemical recipe so advanced that we are only now beginning to crack its code. The secret lies in a specific, intentional mixture. Roman engineers combined slaked lime with a special type of volcanic ash known as pozzolana, found near the city of Pozzuoli. But the real masterstroke was the final ingredient: seawater. Instead of using fresh water, they mixed their concrete with the sea itself. When this combination happens, a remarkable chemical process called a pozzolanic reaction takes place. The lime and the silicate-rich ash, in the presence of salt water, form a crystalline structure that is incredibly dense and resilient. But the true magic is in its ability to self-heal. If a tiny crack forms and seawater seeps in, it actually triggers the formation of new crystalline minerals that fill the gap, effectively healing the wound. It's a material that possesses a kind of built-in immune system. Compare this to modern Portland cement, the backbone of contemporary construction. Our concrete is fundamentally brittle. When saltwater infiltrates it, the reinforcing steel inside rusts and expands, causing the concrete to crack and spall apart from the inside out. The Roman recipe, by contrast, created a monolithic, rock-like mass that actually benefits from its interaction with the marine environment. For centuries, historians and engineers assumed the durability of Roman concrete was a happy accident, a lucky combination of local materials. But recent analysis by materials scientists points to a much more startling conclusion. This was deliberate chemical engineering. The Romans may not have understood the atomic-level interactions, but through centuries of trial and observation, they perfected a formula that we, with all our analytical power, are still trying to perfectly replicate. The implications are profound. This was not primitive technology. It was a lost science of material durability, a testament to a level of practical chemistry that vanished for over a millennium. It makes you wonder what other secrets are locked away in the stones of other ancient cultures, waiting for us to look closely enough. The Romans may have mastered the chemistry of concrete, but another ancient mystery lies in the physics of pure stone. Moving from the blended compounds of the Roman harbors, we encounter a challenge that seems to defy the very tools we believe these cultures possessed: the impossible precision of megalithic stone cutting. How do you take some of the hardest stones on Earth, granite, basalt, diorite, and shape them with a level of accuracy that would be impressive even with computer-controlled diamond saws? This is not about brute force, it is about a finesse that leaves modern stonemasons both baffled and in awe. Sites like Picchu in the highlands of Bolivia present a scene that looks less like an archaeological ruin and more like a stonemason's workshop hit by a bomb, with the crucial difference that the scattered pieces are masterpieces of fabrication. We find andesite blocks, a stone as hard as steel, carved with perfect right angles, impossibly straight grooves, and complex geometric channels that interlock like pieces of a grand stone puzzle. Similarly, the granite casing stones of the Great Pyramid, now mostly gone, were reportedly so perfectly fitted that a razor blade could not be inserted between them. The conventional explanation of copper chisels and stone hammers begins to feel woefully inadequate when faced with such evidence. Copper is a soft metal, utterly useless for cutting granite with any efficiency, let alone achieving mirror-smooth surfaces. So, if not simple pounding and grinding, what methods did they use? This question has spawned a range of theories, some controversial, all attempting to solve this ancient fabrication puzzle. One compelling idea involves the use of advanced abrasives. While they may not have had hardened steel, they did have access to a substance harder than almost anything: diamond. Sand containing diamond dust, or even diamonds set into the tips of drilling tools, could theoretically account for the precise cuts and boreholes found in ancient Egyptian artifacts. We have evidence of tubular drilling in granite where a core of stone is cleanly removed, leaving behind a spiral groove that suggests a consistent, powerful cutting action. Another theory points to the power of sound. Could specific sonic vibrations have been used to somehow soften stone or guide a cutting tool with incredible precision? While it sounds like science fiction, we know that certain resonant frequencies can affect materials, and some researchers point to ancient legends and carvings that might hint at such lost acoustic technologies. A more down-to-earth, yet equally ingenious proposal involves chemical knowledge. Certain plants produce acids that can weaken the crystalline structure of stone. If ancient builders discovered a way to create a paste from such plants and apply it to a stone's surface, they could have effectively softened the outer layer, making it easier to work with simpler tools. The goal of all this precision was far more than just showing off. It was a matter of structural survival. In earthquake-prone regions like the Andes, the interlocking, mortar-less joints of Inca walls were a brilliant engineering solution. During a tremor, the stones in a wall like that at Sacsayhuaman or Ollantaytambo can actually shift and sway slightly, dancing with the seismic energy before settling back into place. A rigid, mortared wall would crack and collapse, but these flexible, precisely fitted assemblies dissipate the energy, allowing the structure to move as a unified, resilient whole. The microscopic analysis of these cut surfaces often reveals tool marks that don't match any known primitive method. They show a consistency and smoothness that suggests a tool moving at a high, steady speed, not the irregular, choppy marks left by hand-held pounding. The tolerances achieved, the gaps between stones measured in thousandths of an inch, are something modern engineers would strive for in precision machinery, not in multi-ton building blocks. This forces a dramatic reconsideration of what we label as primitive. These societies may not have had electricity or internal combustion engines, but their understanding of material science, geometry, and structural physics was in its own way profoundly advanced. They developed a technology perfectly suited to their environment and their ambitions, a technology of stone that has endured long after the empires that built them have turned to dust. So we've seen how ancient builders mastered materials, creating concrete that heals itself and cutting stone with impossible precision. But what happens when the ground itself decides to fight back? This brings us to a third and perhaps most life-saving material mystery, the secret of anti-seismic foundations. It's a terrifying fact of geology that some of the most desirable places for human civilization, fertile river valleys, coastal plains, and mountain passes, are also some of the most seismically active. Yet, time and again, we find ancient cities in these very zones that have withstood earthquakes which have completely demolished their modern successors. This isn't a matter of luck. It's evidence of a brilliant, calculated approach to engineering that understood how to work with the Earth's violence rather than simply resist it. The conventional approach to building for much of recent history has been to create structures that are as rigid and strong as possible, to try and out-muscle an earthquake. Ancient engineers, in their profound wisdom, understood that this is a losing battle. You cannot defeat the immense energy of a tectonic shift. Instead, their genius lay in designing foundations that could absorb that energy, dissipate it, and let the building dance with the tremors rather than stand rigid and break. One of the most widespread techniques was the use of what we would now call a sacrificial layer or a sliding plane within the foundation itself. Archaeologists excavating Minoan palaces on Crete, like the great complex at Knossos, have found evidence of sophisticated foundational mats. Beneath the heavy stone walls, builders would place alternating layers of stone, clay, and even sand. During an earthquake, these layers would allow for a small amount of lateral movement. The foundation could slide and shift minutely on this flexible bed, isolating the upper structure from the worst of the ground's shaking. Imagine trying to snatch a tablecloth off a table set with fine china. If you yank it quickly and smoothly, the cloth slides out and the plates, thanks to their inertia, stay largely in place. This ancient technique operates on a similar principle, though on a much slower, more violent scale. The ground jerks, the foundational layers absorb and redistribute that jerk, and the building above experiences a dampened, less destructive motion. In some Greek structures, there is even evidence of thin sheets of lead being used in these foundational sandwiches. Lead is a malleable metal that can deform under pressure and then rebound, acting as a fantastic shock absorber. This is not a technology we would associate with the Bronze Age, yet there it is, a deliberate design choice for stability in a volatile world. But perhaps the most iconic example of this ancient seismic wisdom comes from the Incan Empire, high in the Andes Mountains. At sites like Machu Picchu and Ollantaytambo, you can witness what engineers today call base isolation in its most elegant Stone Age form. Look closely at the famous Inca walls, those breathtaking jigsaw puzzles of perfectly fitted stone. You'll notice that the individual blocks are not simple rectangles. They are polygonal with multiple sides and angles that interlock in a complex three-dimensional web. Crucially, the stones are often slightly trapezoidal, leaning inward, and the walls themselves taper upward. This isn't just an artistic choice, it's a highly functional one. During an earthquake, a rigid, rectangular wall wants to pivot at its base and collapse outward. But an Incan wall, with its interlocking stones and inward lean, behaves differently. The stones are not mortared together. They are held in place solely by gravity and their precise fit. When seismic waves hit, the entire wall can flex. The stones micro-shift, they dance against each other, dissipating the energy through friction and movement. Once the shaking stops, gravity simply pulls each uniquely shaped block back into its original, locked position. It's a self-centering system carved directly into granite. The Incas understood harmonic motion and dynamics on an intuitive level. They designed their structures to have a certain natural frequency of vibration that would counteract or dampen the destructive frequencies of the earthquakes common to their region. They were, in effect, building the ancient equivalents of the sophisticated base isolators used in modern skyscrapers and bridges today. Systems that use alternating layers of rubber and steel to allow a building to sway safely during a quake. The brilliant simplicity of the Inca solution is that their isolation system is the structure itself. There are no separate parts to maintain or replace. The wisdom is embedded in the geometry of every stone, a permanent and resilient feature. These were not accidental discoveries or happy coincidences. The consistent application of these techniques across vast empires and thousands of years points to a codified body of knowledge passed down through generations of master builders. They observed how the earth moved, they learned from failures, and they developed a repeatable, sophisticated engineering philosophy aimed at longevity and safety. This adaptive design, this willingness to yield in order to survive, represents a pinnacle of ancient genius, and this same philosophy of working in harmony with natural forces extended brilliantly to another fundamental element, one just as powerful and destructive as the shaking earth, water. This mastery of managing the Earth's movement leads us directly to another fundamental force that ancient engineers had to contend with: water. For any city, water was a double-edged sword. It was the absolute essential for life, for agriculture, for ritual, and for cleanliness. Yet, in its excess, it was a relentless destroyer, capable of eroding foundations, flooding streets, and breeding disease. The true mark of an advanced civilization, therefore, was not just finding a water source, but mastering its every movement from the ground up. The foundation of a city was not merely a platform for buildings. It was the very heart of a complex hydraulic system, a hidden circulatory network designed to give life and prevent decay. To see this principle in its full glory, we must travel to one of the world's earliest and most meticulously planned cities, Mohenjo-Daro in the Indus Valley, which thrived over 4,000 years ago. Walking through its excavated streets is like reading a blueprint for urban water management. Every single house, from the largest to the most modest, was connected to a city-wide drainage system. Earthenware pipes carried wastewater from bathrooms and kitchens out into covered brick-lined drains that ran beneath the main streets. These drains were designed with clever features we still use today. They had manholes for periodic cleaning and maintenance, and they were gently sloped to ensure a constant flow, preventing blockages. This wasn't a haphazard addition. It was an integral part of the city's foundational plan, laid down before the streets were even paved. It speaks to a profound understanding of public health and civic engineering on a scale that would not be seen again in many parts of the world for thousands of years. But managing wastewater was only one part of the equation. A city also needed a reliable supply of clean, fresh water. Here, too, ancient engineers showed remarkable foresight. At the Minoan Palace of Knossos on Crete, archaeologists uncovered a system that rivals modern municipal waterworks. They built terracotta pipes that were so well designed, tapered at one end to create a tight, pressure-resistant fit, that they could effectively move water uphill using principles of gravity and siphonage. These pipes connected to sophisticated aqueducts and deep stone-lined wells, ensuring a constant flow for drinking, bathing, and even elaborate flush toilets within the palace. This demonstrates a move beyond simple survival to a clear desire for comfort and sanitation. Perhaps the most critical hydraulic challenge, however, was protection from the outside. A sudden downpour or a seasonal flood could be catastrophic, washing away the carefully laid foundations of an entire city. The engineers of Mohenjo-Daro addressed this with breathtaking ambition. The entire city was built on a massive, artificial mud brick platform, a raised citadel that lifted it high above the floodplain of the Indus River. This was foundational engineering on a colossal scale, a deliberate act of reshaping the landscape for permanent security. Furthermore, the layout of the city itself was a tool for water management. The streets were not flat, they were precisely graded. They sloped gently but consistently, directing rainwater away from residential areas and into the main drainage channels. Even the central courtyards and plazas were subtly angled to function as collection basins, ensuring that not a drop of water would sit and stagnate, undermining the brick and earth foundations with destructive dampness. This reveals a holistic, city-wide master plan where every element, every street, every building, every pipe was part of an integrated environmental system. The ancient hydraulic engineer did not see a foundation as a separate thing from the water system. The water system was the foundation. It was the hidden infrastructure that kept the city alive, healthy, and standing firm against the elements. This ability to manage the flow of liquids, to direct the very course of nature beneath their feet, was a testament to a systemic way of thinking that would be applied to an even more immense physical challenge: the sheer, crushing weight of their own monumental constructions. After mastering the flow of water, ancient builders turned their attention to an even more fundamental force: the relentless, constant pull of gravity. The most iconic and enduring symbols of their success are the colossal pyramids and raised platforms found across the globe. These structures are not just monuments to ego or piety. They are profound lessons in the art of load-bearing, masterclasses in distributing unimaginable weight to prevent their own collapse. Consider the foundation of the Great Pyramid of Giza, a near-perfect square covering 13 acres. The weight of the 2.3 million stone blocks it contains is almost incomprehensible, estimated to be around 6 million tons. If that immense load were concentrated on a small area, the entire structure would have sunk into the desert sand within a generation, like a heavy stone dropped in mud. The pyramid's genius lies in its brilliant geometry. The wide, sprawling base acts like a giant snowshoe, spreading that colossal weight over a vast area. This dramatically reduces the pressure on any single point of the ground beneath it. The sloping sides then channel the gravitational forces downward and outward in a stable, balanced manner. It's a principle of physics that we formally understand today, but the builders of Giza applied it with an intuition that borders on the supernatural. They understood that to build high, you first had to build wide, creating a stable foundation that could shoulder the burden of ambition. But before a single stone of the pyramid was laid, an even more critical phase of work took place, one that is often overlooked: the preparation of the ground itself. The Giza Plateau is not a perfectly flat, naturally occurring table. The ancient Egyptian engineers had to make it one. Through painstaking effort, they leveled the entire bedrock foundation to an almost unbelievable degree of accuracy. Surveys have shown that the base of the Great Pyramid is leveled to within just 2.1 centimeters, or less than an inch, across its entire 13-acre surface. Imagine achieving that kind of precision over such a vast area using only simple tools like water-filled trenches and sighting rods. This meticulous leveling was not for aesthetic reasons. It was absolutely essential for structural integrity. An uneven foundation would have created points of uneven stress as the pyramid rose, leading to cracks, shifts, and potentially a catastrophic failure. By ensuring the bedrock was perfectly level, they created a uniform starting point, guaranteeing that the weight of the entire structure would be transferred evenly into the earth. This careful preparation transformed the natural limestone plateau into a flawless, integral part of the building itself. The construction itself was a process of building a stable, unified mass. The pyramids were not hollow shells filled with rubble. They were built in layers or courses, with each layer acting as a complete and stable structure in itself. As each new course was added, it compressed the one below, creating a monolithic mass that behaved almost like a single, gigantic stone. This is where the true sophistication reveals itself, particularly in structures like the Great Pyramid that contain complex internal networks of chambers and passages. At first glance, carving out large rooms deep within a mass of stone seems like it would weaken the entire edifice, and it would if done without understanding. The builders demonstrated an advanced knowledge of structural integrity by designing these voids with incredible care. The king's chamber, for instance, is capped by 5 sets of enormous granite beams, arranged in a staggered, gabled formation above the ceiling. This brilliant design creates a reliving chamber, distributing the immense weight of the masonry above away from the ceiling of the chamber itself and channeling it down through the massive walls surrounding the room. It's an ancient precursor to the structural principles we use in bridges and buildings today, knowing exactly where and how to remove material without compromising the strength of the whole. This was the opposite of brute force architecture. It was a delicate, calculated balancing act, a dance with physics on a scale that is still awe-inspiring. The confidence to undertake such a project, to believe that this mountain of stone would stand for eternity, could only have come from a deep, intimate knowledge of the land, the materials, and the immutable laws of nature. This profound understanding of the earth is perfectly illustrated by a city that seems to defy gravity itself, not by spreading its weight, but by becoming one with the mountain it sits upon. This philosophy of working with the weight of the earth finds its ultimate expression not on a flat desert plain, but on a knife-edge ridge high in the Andes. Machu Picchu is more than a beautiful ruin. It is a masterclass in geotechnical engineering, a place where the line between the built and the natural world completely dissolves. Perched more than 2,000 meters above sea level, straddling a saddle between 2 sharp peaks, its very existence seems to defy logic. How could a city of this scale be built on such a precarious, landslide-prone slope and still be standing perfectly intact more than 5 centuries later? The answer lies not in the walls you see, but in the mountain you stand on, because the Incas didn't just build on the mountain, they rebuilt the mountain itself to be its own foundation. The first and most crucial step was a monumental act of landscaping. Before a single stone was laid for a temple or a house, armies of workers began sculpting the steep slopes into a series of vast, flat terraces. To our modern eyes, these terraces look like agricultural fields, and they certainly served that purpose, but their primary function was far more fundamental. They were massive, reinforced retaining walls that created a stable artificial plateau. These were not simple garden beds. Their construction was an engineering project of staggering ambition. The Incas would first build a sturdy stone wall at the downhill edge of a terrace, sometimes reaching depths of 3 meters or more. Behind this wall, they would lay down a deep foundation layer of large stones for drainage, followed by a layer of smaller gravel, then sand, and finally topsoil. This complex, multi-layered system acted like a giant sponge and a shock absorber. It provided a level building platform on an impossibly steep grade, but more importantly, it prevented the entire mountainside from sliding away during the heavy seasonal rains that drenched the region. The terraces were the city's deep, subterranean anchor, a grid of stability carved directly into the geology of the site. But building these terraces was only half the battle. The real genius of Machu Picchu lies in what happened to the water. In the cloud forest environment of the Andes, torrential rainfall is a constant threat. If water is allowed to pool or seep into the ground behind a retaining wall, it creates hydrostatic pressure, a force that can build up and push the wall outward until it catastrophically fails. The Incas understood this phenomenon intimately. Their solution was a hidden circulatory system that would make a modern civil engineer proud. Beneath every terrace, woven throughout the foundation layers, was a sophisticated network of drainage. They didn't just hope the water would find its way out, they actively and intelligently directed it. The bottom layer of large stones in each terrace functioned as a French drain, giving water a clear, easy path to flow. This water was then channeled into a city-wide system of stone-lined canals and culverts that ran underneath the pathways and plazas. These channels were carefully sloped to carry the water away from the structures and safely off the side of the mountain. During a downpour, the city didn't flood. It literally drank the water, channeling the potential destroyer through its very bones and harmlessly away. This ensured that the foundation layers remained dry and stable, preventing the soil from becoming waterlogged and heavy, which would have placed unbearable stress on the retaining walls. It was a proactive, not a reactive system. The water management at Machu Picchu is so effective that to this day, during the rainy season, the site remains remarkably stable while modern roads carved into nearby mountainsides often wash away. This deep partnership with the mountain is most beautifully visible in the stonework itself. Look at any of the major structures at Machu Picchu, and you'll see that the builders made no attempt to level the ground completely. Instead, they incorporated the natural contours of the bedrock directly into their architecture. Giant, living outcrops of granite were not quarried away. They became the foundational cornerstones of buildings. Walls were built to flow around these outcrops, sometimes with niches carved directly into the living rock. In the Temple of the Sun, a massive, sculpted stone altar is seamlessly integrated with the natural bedrock below it, creating a single, monolithic entity. This wasn't just a symbolic gesture of reverence for the earth. It was a brilliantly practical structural technique. By tying their masonry directly to the most stable part of the mountain, the bedrock itself, they created an unbreakable bond. The man-made walls and the natural mountain became a unified structural system, moving together as one during seismic events. This is the Incan anti-seismic principle we discussed earlier, applied at the most fundamental level. The city was literally rooted to the earth, its foundations an extension of the mountain's own bones. This approach reveals a profound respect for the terrain. The Inca engineers did not see the challenging topography as an obstacle to be conquered with brute force. They saw it as a partner. They listened to the land, understood its strengths and its weaknesses, and designed their city to work in harmony with them. They stabilized the slopes, managed the water, and married their structures to the immovable bedrock. In doing so, they built a city in a location that would give modern engineers pause. A city that has endured not in spite of its environment, but because of its symbiotic relationship with it. This harmonious approach stands in stark contrast to the mindset required for a completely different, yet equally audacious feat of foundational engineering, building a majestic city not on solid rock, but on the soft, shifting, and seemingly impossible ground of a swamp. While the Incas mastered the art of building with a mountain, other cultures faced the opposite challenge, the complete absence of solid ground. Imagine the audacity required to found a great city not on a mighty cliff or a stable plain, but on a swamp. This was the reality for the builders of two of history's most magnificent water cities, Venice in the lagoons of the Adriatic Sea, and Tenochtitlan, the Aztec capital rising from the waters of Lake Texcoco. Their solutions to this seemingly impossible problem are masterpieces of adaptive engineering, born from a deep understanding of their local environments and a refusal to be limited by nature's constraints. The Venetians and the Aztecs never met, separated by an ocean and centuries, yet they arrived at similarly ingenious answers to the same foundational riddle. Their methods, however, could not have been more different, reflecting a fascinating divergence in approach. Venice chose to pin itself to the earth with immense force, while Tenochtitlan learned to float upon it, gradually convincing the water to become land. The story of Venice's foundation is one of monumental perseverance. The early settlers of the Venetian lagoon were faced with a treacherous base of soft, waterlogged silt and mud, a substance completely incapable of supporting the weight of stone buildings. Their solution was as straightforward as it was staggering in its scale. They would drive through the unstable layer to find something solid beneath. That solid layer was Caranto, a dense, compacted clay stratum lying several meters below the mud. To reach it, they employed a technique that would define the city for over 1,000 years: pilings. Millions upon millions of tree trunks, primarily alder and larch wood known for its water-resistant properties, were sharpened and driven deep into the mud by teams of workers using massive drop hammers. These piles were packed so tightly together that they formed a submerged forest, a hidden artificial reef upon which the city would rest. But this was only the first step. Once the piles were in place, wooden platforms were constructed on top of them, creating a stable, level surface. On these platforms, the Venetians built their stone foundations. The true brilliance of this system lies in its chemical longevity. The soft, oxygen-poor mud of the lagoon is an anaerobic environment. This lack of oxygen prevents the growth of the fungi and bacteria that would normally cause wood to rot. Instead of decaying, the wooden piles petrified over centuries, gradually hardening into a stone-like state through a process of mineral saturation. This was an unplanned marvel of material science. The very environment that made the ground unstable also perfectly preserved the material used to stabilize it. The weight of the buildings above actually helped, compressing the piles and the mud around them into an increasingly solid mass. St. Mark's Basilica, for instance, is said to rest on a foundation of over 1 million of these wooden piles. It is a city literally standing on a preserved forest, a testament to an engineering philosophy that sought to conquer the swamp through sheer force of numbers and depth. Across the Atlantic, the Aztecs faced a similar challenge in the vast lake system of the Valley of Mexico, but their philosophy was not one of conquest but of cooperation. When they arrived at Lake Texcoco, they found a shallow, marshy environment. Instead of trying to pin themselves to a non-existent solid bottom, they embraced the water, learning to build upon it. Their ingenious invention was the chinampa, often called floating gardens, though that term is a bit misleading. A chinampa was, in essence, an artificial island. The construction process was a masterclass in sustainable, layered engineering. First, artisans would stake out a rectangular plot in the shallow lake bed, using a fence of woven reeds and wooden posts. This enclosure was then filled with layers of organic material. They would pile up lake mud, rich in nutrients, and alternate it with layers of decaying vegetation and aquatic plants. This created a buoyant, compost-rich base that was actually above the waterline. To secure the edges and prevent the new island from eroding, they planted willow trees all around the perimeter. The willow roots would quickly grow down through the layered materials, weaving a dense, living net that bound the entire chinampa together, creating a solid, root-reinforced foundation. Over time, as the organic matter compacted and the root systems strengthened, these islands became permanent, stable pieces of land. The channels of water between the chinampas acted as natural canals for transportation, but they also served a crucial hydraulic purpose. They allowed for a constant capillary action, drawing water up to the roots of the crops grown on the chinampas, creating an incredibly fertile and self-watering agricultural system. The Aztecs expanded their capital, Tenochtitlan, by systematically creating a grid of these chinampas, gradually reclaiming land from the lake in a way that was both productive and structurally sound. The foundation of Tenochtitlan was not a static, rigid platform like Venice's. It was a living, breathing, growing entity. It was a foundation built from the lake itself, a perfect symbiosis between human need and the natural environment. When we place these two solutions side by side, the contrast is illuminating. Venice represents a top-down, intensive intervention. It required the mass harvesting of forests and the laborious driving of piles to force a stable base into an unwilling environment. It's a powerful, almost aggressive approach to foundational engineering. Tenochtitlan, by contrast, exemplifies a bottom-up organic strategy. The Aztecs used readily available local materials, reeds, mud, and plants, and worked with the lake's ecosystem to create a foundation that grew and solidified over time. It was a patient, accretive process, yet both methods were brilliantly adaptive. The Venetians used the water-resistant larch wood available in the forests of the nearby mainland, while the Aztecs used the reeds and mud that were right at their fingertips. Both cities in their heyday were marvels of urban planning, with intricate canal networks and magnificent stone structures that belied their soft-footed beginnings. They proved that a challenging environment was not a barrier to greatness, but rather a catalyst for innovation. It forced human ingenuity to reach new heights, leading to foundational solutions that were as beautiful and complex as the cities they supported. The silent, preserved forest beneath Venice and the living, root-bound earth of the chinampas stand as enduring monuments to the idea that where we choose to build does not limit what we can achieve. It only defines the unique path we must take to get there. Imagine an approach to architecture so radical that it eliminates the single greatest risk in construction, the foundation itself. Instead of piling stone upon stone, carefully balancing weight on prepared ground, what if you could simply convince the mountain to become your building? This is the breathtaking reality of the bedrock cities, where the very idea of a foundation is turned inside out. At places like Petra in Jordan and Lalibela in Ethiopia, ancient builders employed a philosophy of subtractive architecture. They didn't assemble their monuments, they revealed them, painstakingly carving facades, chambers, and entire churches directly from the living rock. In doing so, they achieved a level of permanence that is almost unimaginable. The foundation was no longer a separate, human-made base. It was the immutable heart of the mountain, offering a stability that no constructed platform could ever hope to match. The structure and its base became a single, monolithic entity, united against the ravages of time and weather in a way that is uniquely defiant. This method, however, came with an immense and unforgiving risk. For a builder working with blocks, a mistake might mean replacing a single stone, but for the sculptors of Petra and Lalibela, there were no second chances. Their process was one of meticulous, irreversible subtraction. Every strike of the hammer and chisel was permanent. A single miscalculation in depth, a misjudgment in the angle of a column, or an error in planning the interior spaces could ruin an entire project, wasting years of labor on an uncorrectable flaw. This demanded a level of foresight and planning that borders on clairvoyance. The architects had to hold the complete, finished form in their mind's eye, seeing the magnificent temple or church hidden within the unshaped cliff face long before the first chip of rock fell away. They were not just builders, they were visionaries performing a kind of architectural archaeology, uncovering a masterpiece that only they could see. Perhaps the most counterintuitive aspect of this technique was the process itself. They carved from the top down. Unlike conventional construction, which builds upward from a foundation, these artisans would begin at the top of the rock face and work their way downward. Imagine sculpting a statue, but instead of starting with a block on a stand, you are standing on a scaffold against a cliff, and your first task is to carve the tip of the highest spire or the peak of the roof. This top-down approach was a stroke of genius born of sheer practicality. It eliminated the need for dangerous and cumbersome scaffolding to reach the upper sections later. More importantly, it prevented the disaster of having rocks and debris from the upper sections falling onto and damaging the finely finished work below. By starting at the top and moving downward, they kept the work area clear and safe, a logical yet profoundly ambitious strategy that required them to fully trust their grand plan. The Nabatean city of Petra provides a stunning example of this subtractive art on a colossal scale. The famous treasury, or Al-Kosneh, is not a building built in front of the rose-red sandstone cliff. It is the cliff itself, intricately carved into a breathtaking Hellenistic facade. The builders exploited the natural geological layers of the rock, using variations in color and hardness to accentuate architectural features, but the true marvel lies inside. Beyond the grand doorway, they hollowed out a series of chambers and halls from the solid mountain, creating interior spaces that are cool, silent, and awe-inspiring. The entire structure stands as a testament to a perfect marriage of human ambition and geological reality. The mountain provides not just the material, but the structural integrity. There is no worry about settling, no fear of the walls separating from the foundation, because the walls are the foundation. Half a world away, in the highlands of Ethiopia, the same principle was applied with a deeply spiritual purpose. The 12 rock-hewn churches of Lalibela are not simply built, they are excavated. Here, the architects went a step further than those at Petra. They did not just carve into a cliff face, they first excavated deep trenches down into the volcanic tough bedrock, isolating a giant block of stone. Then, from this free-standing block, still attached to the earth at its base, they meticulously carved out both the exterior and interior of the church, creating freestanding pillars, windows, arches, and roofs, all from a single, continuous piece of rock. The Church of St. George, shaped like a perfect Greek cross, is the most iconic. It sits at the bottom of a deep, man-made pit, a magnificent structure that was literally revealed by removing everything that was not the church. This method created a foundation of unparalleled solidity. The church is not on the bedrock, it is of the bedrock. It experiences the same thermal expansion and contraction as the earth it is part of, moving in perfect harmony with the ground beneath it, immune to the stresses that plague conventional buildings. This is the ultimate fusion of architecture and geology, a permanent and profound connection to the earth that has allowed these sacred spaces to endure for nearly 1,000 years. This incredible mastery of rock, this ability to command the very substance of the mountain, points to a truth that goes beyond engineering. It forces us to consider the immense human effort, the vast and complex social organization that was required to bring such visionary projects to life. These breathtaking monuments of stone, from the pyramids to the massive heads of the Olmec, present us with a dual mystery. We have marveled at the engineering, at the precise cuts and the brilliant foundational designs. But this forces an even bigger question. How did they manage the people? The physical foundation of these ancient wonders is only half the story. The other half, just as impressive, is the human foundation, the vast, invisible web of logistics, organization, and collective will that had to be in place before the first stone could ever be quarried. The engineering marvels we stand in awe of today were, first and foremost, marvels of human organization on a scale that is difficult to comprehend. Consider the sheer numbers. The Great Pyramid of Giza is estimated to have required a workforce of tens of thousands, not for a few months but for decades. This was not a disorganized mob of slaves, as outdated Hollywood depictions would have us believe. Archaeological evidence, such as the workers' tombs and bakery complexes found near Giza, paints a very different picture. These were likely seasonal laborers, skilled and unskilled, who would work on the monument during the annual inundation of the Nile when farming was impossible. They were housed in sprawling, purpose-built barracks, fed a diet of bread, fish, and beer produced on an industrial scale, and cared for by a support system of medics and priests. This was a state-sponsored project that required a bureaucracy capable of managing a small city dedicated solely to construction. There had to be administrators to coordinate the work gangs, accountants to track the distribution of tools and food, and engineers to design the ramps and levers. This level of specialization implies a sophisticated, centralized society with a stable economic surplus that could feed and clothe thousands of people who were not directly involved in food production. The pyramid itself is the ultimate proof of this organizational capability. The challenge of moving the materials is perhaps an even greater testament to this logistical genius. Take the colossal stone heads created by the Olmec civilization in ancient Mexico. These basalt monoliths, weighing up to 20 tons, were quarried from the Tenochtitlan Mountains. The incredible part, the nearest Olmec centers are over 100 kilometers away, across rivers, swamps, and dense jungle. The Olmec did not have the wheel, nor did they have draft animals like oxen or horses. So how did they do it? The most plausible theory involves a combination of brute force and brilliant ingenuity. It's believed that they transported the massive stones using a system of log rollers and sledges. Teams of workers would have laid down a track of logs in front of a sledge carrying the stone, constantly moving the logs from the back to the front as the sledge inched forward. For river transport, they likely built massive barges, perhaps made of reeds or hollowed-out logs, using the natural current and manpower to float these immense weights downstream. This wasn't a one-time feat, it was a regular, managed operation. It required pathfinders to clear the route, carpenters to maintain the sledges and rollers, and coordinators to manage the teams of pullers in a synchronized effort. The successful transport of a single head was a monumental achievement in project management. The movement of dozens of them points to a society that had mastered the art of large-scale logistics. This human infrastructure was the true bedrock of every ancient mega-project. Without the organized effort of countless individuals, the quarrymen, the transporters, the cooks, the coordinators, the physical foundations we admire would never have been laid. The stones did not move themselves. The pyramids did not rise by magic. They are the direct result of a society's ability to harness its collective labor and direct it toward a single, monumental goal over generations. This scale of collective action reveals something profound about these cultures. It tells us they possessed not just technical knowledge, but also sophisticated social structures, a shared belief system that motivated participation, and economic systems complex enough to support such endeavors. The ability to plan for a project that would not be completed within the lifetime of its original architects speaks to a powerful sense of legacy and a deep connection to the future. This incredible organizational machine, however, was guided by a very specific kind of knowledge, one that looked not just to the earth, but to the heavens for its ultimate blueprint. But the ambitions of these ancient builders reached far beyond the earthly plane. After orchestrating the labor of thousands and mastering the weight of mountains, they turned their gaze upward, seeking to anchor their creations not just to the ground, but to the cosmos itself. For them, the foundation was more than a physical base. It was a sacred interface, a point of connection between the human world and the divine order of the heavens. The precise orientation of a temple or a city was not an arbitrary decision. It was a deliberate act of celestial engineering, a way of weaving the immutable cycles of the universe into the very fabric of their civilization. This practice transforms sites like Stonehenge on the Salisbury Plain, the Great Pyramid of Giza, and the sprawling Temple of Karnak in Egypt from mere structures into colossal stone calendars and astronomical observatories. The Great Pyramid, for instance, is aligned to the 4 cardinal directions with an accuracy that baffles surveyors even today. Its north-south axis is misaligned by an almost negligible fraction of a degree, a level of precision that suggests a profound understanding of the Earth's rotation and the movement of the stars. Similarly, the main axis of the Temple of Karnak is oriented so that on the winter solstice, the sunrise would illuminate the innermost sanctuary, a dramatic event that would have reinforced the pharaoh's divine connection to the sun god Ra. At Stonehenge, the arrangement of the massive sarsen stones creates specific sightlines that frame the sunrise on the summer solstice and the sunset on the winter solstice, marking the turning points of the year with stone-cold certainty. This was not simply about marking time for agricultural purposes, though that was certainly a benefit. It was about embedding a cosmic legitimacy into the foundation of their power. By aligning their most important structures with the solstices, equinoxes, or the rise of a significant star like Sirius, the builders were making a profound statement. They were asserting that their kingdom, their temple, their city was in harmony with the fundamental laws of the cosmos. Its existence was not just sanctioned by the gods, it was a reflection of the eternal order of the universe itself. This conceptual alignment granted a permanence that went beyond physical durability. Even if the walls were to crumble, the foundational principle, the connection to the heavens, would remain etched into the landscape for eternity. Achieving this celestial precision required a sophisticated scientific tradition long before the invention of the telescope or the compass. The initial act of surveying, of laying out that first, crucial foundation stone in its astronomically correct position, was a feat of both patience and profound knowledge. Imagine the scene, a team of priest astronomers on a vast, empty plain, tasked with marking a line that points true north or directly toward the rising sun on the longest day of the year. Their tools were deceptively simple, yet incredibly effective. One of the most fundamental was the gnomon, essentially a vertical rod stuck into the ground. By meticulously tracking the length and direction of the shadow it cast throughout the day and across the seasons, these ancient scientists could determine true north and south with remarkable accuracy. The shortest shadow of the day points due north, while the longest and shortest shadows over a year mark the solstices. For more precise alignments over longer distances, they likely used a method involving sighting lines. This could involve placing a series of marker poles in a straight line toward a celestial target, such as a particular star rising on the horizon. By observing the star's position over many nights and adjusting the markers accordingly, they could establish a reference line of astonishing accuracy that could stretch for miles. The mathematical principles behind this were equally advanced, even if they weren't written down in the way we know today. The use of the Pythagorean theorem, embodied in the simple 3:4-5 triangle ratio to create perfect right angles, is evident in the precise corners of Egyptian and Mesopotamian structures. This combination of practical astronomy and applied geometry allowed them to translate cosmic patterns into terrestrial blueprints. The laying of the foundation stone was therefore a ritual of immense importance, a ceremony that fused science and religion. It was the moment when the abstract order of the sky was made concrete and permanent on the earth. This act transformed the building site from a random patch of ground into a sacred center, a microcosm of the universe, ensuring that every stone laid thereafter would participate in that grand celestial harmony. So we've seen how ancient builders aligned their foundations with the cosmos, but that immediately presents another, even more practical mystery. How did they translate those celestial observations into such breathtakingly precise terrestrial measurements? How do you take a line pointing to a star on the horizon and use it to lay out a foundation that is perfectly square and perfectly level across an area the size of a small town, all without a single modern instrument? The answer lies not in magic, but in a suite of ingeniously simple tools and a deep, practical grasp of geometry that would make any modern engineer nod in respect. Let's start with the challenge of creating a perfect right angle. For the Egyptians constructing the Great Pyramid, ensuring that the corners were exactly 90 degrees was absolutely critical. A tiny error at the base would multiply into a catastrophic misalignment at the apex. They likely used a method so elegant it's still taught in schools today, the 3:4-5 triangle. This is a direct application of the Pythagorean theorem, centuries before Pythagoras was born. A rope with knots spaced evenly at 3, 4, and 5 units could be stretched taut around 3 stakes. When the distance between the first and second stake is 3 units, between the second and third is 4 units, and the distance between the first and third stake measures 5 units, you have guaranteed yourself a perfect right angle at the corner where the 3 and 4 unit sides meet. By scaling this principle up using longer ropes with knots at 12, 16, and 20 units for instance, they could create massive, perfectly square layouts for their monuments with nothing more than rope and stakes. This was applied mathematics on a grand scale, but creating right angles for buildings is one thing, laying out an entire landscape is another. The Romans, masters of organization and empire building, faced this challenge on a colossal scale. When they established new cities or divided conquered land into neat, rectangular plots for their colonists, a process called centuriation, they needed a tool that could rapidly and accurately create straight lines and right angles over miles of countryside. Their solution was the groma. This deceptively simple device consisted of a vertical staff with a horizontal crossarm. From the end of each arm hung a plumb bob, a weight on a string that would always point directly toward the Earth's center. A surveyor would plant the staff in the ground and sight along the pairs of plumb lines. By aligning one set of bobs with a known reference point, he could then use the perpendicular set to mark a perfect 90-degree line. A team of assistants would then place markers along this sight line, creating the straight roads and property boundaries that became the signature of Roman order across Europe. The groma was the ancient equivalent of a theodolite, a portable instrument that turned the abstract concept of a right angle into a tangible, repeatable action on the ground. Of course, right angles are useless if your foundation isn't level. Imagine trying to build the Great Pyramid on a base that slopes even slightly. The entire structure would lean and eventually collapse. The achievement of leveling the Giza Plateau to within 2.1 centimeters, or less than an inch, across its entire 13-acre base is a feat that still staggers engineers today. How was this humanly possible? The tool they almost certainly used was the water level. The principle is beautifully straightforward. Water always finds its own level. An ancient builder could use a simple trench dug around the perimeter of the construction site, fill it with water, and then measure down from the water's surface at various points to determine the high and low spots of the bedrock. Alternatively, they might have used a long, narrow trough of water or even a series of connected pots. By marking a consistent height on a stake at the waterline in one location, they could carry that identical reference point to every other corner of the site, ensuring that every measurement was made from the same perfectly horizontal plane. This method, while simple in concept, required immense patience and meticulous attention to detail, but it was foolproof. It demonstrates a profound understanding of basic physics, harnessing a fundamental law of nature to achieve a precision that seems almost impossible for the time. For the most critical alignments, particularly those to the stars, the Egyptians employed another specialized tool, the Merkit. This instrument, whose name means indicator, was used by priest astronomers to track the passage of time and the movement of celestial bodies. The setup involved a pair of merkits, which were essentially notched palm ribs used in conjunction with a plumb line. One priest would sight a specific star through the notch of his merkit, while another, positioned some distance away, would do the same. By carefully noting when the star crossed the meridian, an imaginary north-south line in the sky, they could establish a true north-south axis with incredible accuracy. This celestial surveying was likely done over many nights to refine the alignment, and once established, this line would become the sacred, unchangeable baseline for the entire foundation of a temple or pyramid. The combination of these tools, the rope for the 3-4-5 triangle, the groma for land division, the water level for flat plains, and the merkit for astronomical alignment, created a complete surveying toolkit. This knowledge wasn't common property. It was the closely guarded secret of guilds of master builders, a professional class who passed their techniques down from generation to generation through apprenticeship. This oral tradition, while effective for maintaining high standards, also made the knowledge incredibly fragile. When empires fell and these professional classes disbanded, their sophisticated techniques could vanish almost overnight, leaving behind only the magnificent, baffling results of their work for future generations to puzzle over. This incredible legacy of knowledge, this sophisticated understanding of materials, physics, and logistics, presents us with one of history's most perplexing puzzles. If these techniques were so brilliant, so effective, why did they vanish? How could entire libraries of practical engineering wisdom, the very secrets that allowed civilizations to build for eternity, simply fade from human memory? The answer is not a single event, but a slow, creeping shadow, the fragile nature of knowledge itself, especially when it is held by a specialized few and dependent on the stability of a complex society. The decline was not an accident. It was a systemic failure that repeated itself across the globe and throughout time. Consider the fall of the Roman Empire in the West, a process that unfolded over several centuries. The Roman world was a vast, interconnected system of trade, administration, and crucially, professional guilds. The knowledge of how to mix the perfect volcanic ash and lime for their self-healing concrete, the techniques for surveying vast territories with the groma, the logistical protocols for managing aqueduct construction, this was not common knowledge. It was the specialized domain of the architectus, the master builder, a professional class trained through rigorous apprenticeships. As the empire's borders contracted, as trade routes were severed by conflict and its economy crumbled, the large-scale public works projects that sustained these builders simply stopped. There was no longer a demand for new harbors, vast aqueducts, or monumental basilicas. The guilds, their funding and purpose gone, slowly dissolved. The master builders either found other work or their knowledge died with them, no longer passed down to a new generation. The recipe for Roman concrete, a cornerstone of their architectural dominance, became a ghost, a legend whispered among later masons who could only look at the crumbling yet enduring Roman ruins and wonder. This loss is starkly visible in the centuries that followed. When the great cathedrals of the Middle Ages began to rise, 1,000 years after the peak of Roman engineering, the masons were essentially starting from scratch. They had to rediscover, through painstaking trial and error, principles of vaulting and buttressing that the Romans had long since mastered. Their structures, while beautiful, often pushed materials to their absolute limits, leading to collapses that would have been preventable with the Roman understanding of weight distribution and material science. The knowledge hadn't just stagnated, it had actively regressed. This pattern of catastrophic loss is not unique to Europe. Look at the conquest of the Americas. When Spanish conquistadors arrived in the Aztec capital of Tenochtitlan, they were witnessing the pinnacle of Mesoamerican urban engineering, a city built on a lake, sustained by chinampas and supplied by elaborate aqueducts. Within a generation, that society was dismantled. The Spanish conquest was not just a military victory, it was a cultural and demographic cataclysm. The smallpox and other diseases they brought with them decimated the population, wiping out elders, artisans, and the living repositories of knowledge. The new colonial rulers had no interest in preserving the indigenous techniques for building on a swamp. They sought to drain the lakes and build a European-style city on what they considered solid ground, often with disastrous flooding consequences. The sophisticated understanding of hydraulic management that had made Tenochtitlan thrive was lost, not through a slow decline, but in a violent, abrupt rupture. The professional classes who managed the chinampas and the canal systems were dispersed, enslaved, or killed, and their intricate knowledge of the local environment died with them. We can trace this phenomenon even further back to the mysterious collapse of the Late Bronze Age around 1200 BCE. Across the eastern Mediterranean, from the Hittite Empire in Anatolia to the Mycenaean palaces in Greece, a constellation of interconnected civilizations imploded within a short period. The causes are still debated: climate change, famine, invasions, systemic collapse, but the result was the same: a dark age. The art of writing, a key tool for preserving complex engineering knowledge, was lost in Greece for centuries. The precise stone cutting and architectural techniques seen in Mycenaean citadels like Turin's were forgotten. When Greek culture re-emerged centuries later, its early architecture was far more modest. The knowledge required to build cyclopean walls had vanished, a casualty of a globalized system that shattered, taking its specialized experts down with it. This recurring pattern tells us something profound and a little unsettling about human progress. Advanced engineering is not a one-way street upward. It is a fragile ecosystem. It requires stability, economic surplus, and a social structure that can support and transmit specialized skills from one generation to the next. When that support system fractures, whether through invasion, plague, economic collapse, or simply a loss of institutional purpose, the knowledge it sustained can evaporate with terrifying speed. It becomes a ghost in the archaeological record, visible only in the silent, enduring stones that we are only now, with our lasers and ground-penetrating radar, beginning to fully appreciate. The fact that we need 21st century technology to decode the brilliance of 2,000-year-old concrete is a humbling lesson. It forces us to ask a provocative question: If such profound understanding could be lost not once, but repeatedly, across different continents and eras, what does that say about the ultimate source of this knowledge? Was it simply the product of slow, cumulative trial and error, or did it spring from a well of insight that we have yet to fully comprehend? The sheer scale and precision of these ancient projects can feel so immense, so beyond what we expect from societies without modern machinery, that it inevitably pushes our imaginations to the brink. When faced with a puzzle of such magnitude, it's only human to search for explanations that match the grandeur of the mystery itself. This has given rise to a fascinating and often controversial realm of thought, one that suggests the answers might lie not in lost human techniques, but in technologies far beyond anything we recognize, perhaps even from beyond our world. The arguments put forward are compelling on the surface. Look at the Great Pyramid of Giza, they say. The alignment to true north is so exact, the squaring of its 13-acre base so perfect, that it seems to demand the use of advanced surveying equipment we simply don't believe the ancient Egyptians possessed. Or consider the mind-boggling work with diorite, a stone harder than iron. How could a civilization using simple copper chisels and stone pounders possibly have carved intricate vases and statues from this incredibly durable material, achieving a polish that looks almost glass-like? For some, the conventional explanations of ropes, ramps, and relentless human labor feel too small, too primitive to account for such flawless results. The gaps in our understanding, the unanswered how questions, become fertile ground for theories of intervention. The idea that a much older, technologically advanced civilization, now lost to the depths of time, passed on its knowledge before vanishing beneath the sea or the ice. Or, in the most dramatic version, that ancient astronauts visited Earth, providing the blueprints and perhaps even the tools to create these enduring monuments. These narratives are powerful because they offer a kind of satisfying symmetry. A mystery of epic proportions is solved by an explanation of equal epic scale. It is crucial, however, to step back and examine the solid evidence that supports a story of profound, but entirely human, ingenuity. Archaeology has not been silent on these matters. At the Giza Plateau, we have found the remnants of the workers' villages, complete with bakeries that produced thousands of loaves of bread and evidence of medical care for injuries. We have discovered the quarries where the stones were cut, and nearby, simple tools like copper chisels and dolerite pounding stones, which show clear signs of wear from being used on granite. Most tellingly, we have found stones left unfinished, with the clear marks of these tools still visible upon them, providing a direct snapshot of the methods in progress. The idea of a lost global civilization also runs into a significant problem: the sheer diversity of ancient engineering styles. The interlocking, mortar-less masonry of the Incas is fundamentally different from the precise block and mortar construction of the Egyptians, which is different again from the cyclopean stonework of the Mycenaeans. If a single advanced source was responsible, we might expect a more uniform technological fingerprint across the world. Instead, what we see are distinct, culturally specific solutions to universal problems like gravity and seismic activity, a pattern that suggests independent innovation and adaptation to local materials and challenges, not the dissemination of a master template. So, where does this leave us? The true mystery may not be a choice between advanced aliens and primitive humans, but something far more intriguing: the astonishing upper limits of human capability when driven by powerful motivation. We must remember the context. For these cultures, building these structures was often tied to the very core of their belief systems, their relationship with the gods, and the eternal legacy of their rulers. This was not a casual public works project. it was a society's ultimate spiritual and political priority, marshalling generations of knowledge, patience, and collective effort. What seems like an impossible feat to us with our focus on efficiency and speed becomes more conceivable when viewed as a multi-generational endeavor, where a slight improvement in technique each year, accumulated over a century, could lead to breathtaking mastery. The real enigma is not necessarily the tools they used, but the sheer force of will, the organizational genius, and the deep, intuitive understanding of physics and materials that were cultivated and passed down through guilds of master builders. This perspective doesn't diminish the accomplishment. In many ways, it elevates it. It suggests that the potential of the unaided human mind, when focused with intense cultural purpose over long periods, may be greater than we have ever dared to imagine. The stones themselves are not asking us to choose between magic and mundane labor. They are challenging us to expand our definition of what is possible through human ingenuity alone. And it is this very challenge that modern science is now, finally, equipped to take up, moving us from the realm of speculation into the clear light of evidence. For centuries, the only way to truly know what lay beneath our feet was to dig. Archaeologists wielded shovels and trowels like surgeons, carefully peeling back the layers of history, but the process was inherently destructive, slow, and limited to small, targeted areas. It was like trying to understand an entire library by reading a single, random page. We were missing the full story, the grand narrative written across the landscape. But today, a technological revolution is fundamentally changing the game, granting us a kind of X-ray vision that allows us to see the secrets beneath the stones without ever breaking the surface. This shift is as profound as the invention of the telescope for astronomy. We are no longer just scratching at the dirt, we are learning to read the entire Earth. Two technologies in particular are acting as our new eyes, LiDAR and ground-penetrating radar, and they are systematically dismantling our old, limited perceptions of the ancient world. Let's start with LiDAR, which stands for light detection and ranging. Imagine flying over a dense, impenetrable jungle like those in Cambodia or Guatemala. From the ground, it's a solid green wall of vegetation, seemingly hiding nothing. But from the air, a LiDAR unit mounted on a plane or drone fires millions of laser pulses every second down toward the forest floor. Most of these pulses hit the leaves and branches of the canopy, but a lucky few penetrate all the way through the small gaps and bounce off the solid ground below. By meticulously measuring the time it takes for each pulse to return, a computer can build an incredibly detailed, three-dimensional map of the actual ground surface, digitally stripping away every single tree, vine, and bush. The result is a bare Earth model, a ghostly landscape of stunning clarity. In Cambodia, around the famous temple of Angkor Wat, this technology revealed a sprawling metropolis that was completely invisible from the ground. What was thought to be a ceremonial center surrounded by jungle was in fact the heart of a vast urban network. LiDAR maps showed a complex grid of roads, canals, and thousands of previously unknown houses, ponds, and smaller temples, all laid out with precise geometric planning. The city of Angkor was not just a temple complex, it was one of the largest pre-industrial cities in the world, a discovery that forced a complete rewrite of Khmer Empire history. Similarly, in the jungles of Central America, LiDAR has peeled back the canopy to reveal that the Maya civilization was far more populous and interconnected than anyone dreamed, with immense agricultural fields, sophisticated water management systems, and highways linking cities across vast distances. It's as if we've been looking at a painting and only focusing on the main subject, but LiDAR has suddenly illuminated the entire, breathtaking background, revealing a world of activity we never knew was there. While LiDAR gives us a god's-eye view of the landscape, ground-penetrating radar, or GPR, allows us to conduct a detailed ultrasound of the Earth itself. Where LiDAR maps the surface, GPR peers beneath it. This technology works by dragging a small antenna over the ground, which sends high-frequency radio waves down into the soil. When these waves hit a change in density, a buried wall, a stone foundation, an empty tomb chamber, or even a different soil layer, a portion of the energy bounces back to the surface and is recorded. By moving the antenna in a grid pattern, archaeologists can build a three-dimensional picture of what's hidden below, like a medical CT scan for the ground. This non-invasive method is perfect for investigating sacred or historically sensitive sites where digging is forbidden or impractical. In the shadow of Stonehenge, GPR surveys have revealed a stunningly complex ritual landscape that extends far beyond the famous stone circle. They've detected the ghostly impressions of massive pits, processional avenues, and even the remains of other, older monuments made of wood, which have long since rotted away, leaving only their faint signatures in the soil. At ancient Roman sites, GPR can map the entire foundational plan of a villa or a town, revealing the layout of rooms, the course of underground water pipes, and the outlines of hidden courtyards without moving a single shovelful of dirt. It can even detect subtle differences in soil compaction, allowing researchers to identify the locations of ancient post holes from long-vanished wooden structures, giving us a glimpse into the architecture of civilizations that built predominantly with perishable materials. GPR is the ultimate tool for seeing the invisible infrastructure, the hidden veins and bones of a city that have been swallowed by time. Together, these tools are transforming archaeology from a science of careful destruction into a science of precise, non-invasive scanning. This is a paradigm shift of monumental importance. Instead of having to guess where to dig and potentially missing the most important features, archaeologists can now survey huge areas with LiDAR to find the most promising sites, and then use GPR to conduct a virtual excavation, planning their actual physical digs with surgical precision. This minimizes damage to the site and maximizes the information gained. We are discovering that our ancestors were far more ambitious than we gave them credit for. The lost cities we are now finding were not small, isolated towns. They were often sprawling, densely populated megacities with a level of urban planning and environmental management that rivals our own. The scale of their achievements is only now becoming clear because for the first time we have the tools to see the full picture. These technological eyes are not just confirming the grandeur we suspected. They are revealing an ancient world of complexity and sophistication that we are only beginning to comprehend, providing the raw data that allows us to move from awe to analysis, to truly understand how these magnificent structures were engineered to last. Armed with the breathtaking new maps created by LiDAR and ground-penetrating radar, we can now see the full scale of ancient ambition. But seeing a structure's footprint is one thing, understanding the invisible forces that have allowed it to stand for millennia is another. This is where the investigation moves from the field into the digital realm, where modern engineers are performing a kind of virtual archaeology. Using some of the most advanced computer simulations available, they are reverse engineering the past, subjecting ancient masterpieces to stresses that would destroy lesser buildings, all within the safety of a computer model. This process is transforming these ruins from static monuments into dynamic laboratories, providing us with quantitative, undeniable proof of their genius. The cornerstone of this digital detective work is a technique called finite element analysis, or FEA. Imagine taking a complex structure like the Parthenon and digitally slicing it into millions of tiny, interconnected cubes or elements. A powerful computer program can then assign specific material properties to each element: how strong the marble is, how much it weighs, how it responds to bending or compression. Once this incredibly detailed digital twin is created, engineers can apply virtual forces to it. They can simulate the relentless pull of gravity over centuries, or most revealingly, they can unleash a digital earthquake. By inputting data from real seismic events, they can watch in slow motion how the stress waves travel through the virtual Parthenon. They can see exactly where the forces concentrate, which columns bear the most load, and how the entire structure twists and vibrates in response. This is not guesswork, it's a precise mathematical experiment, and what these simulations consistently reveal is that the architectural choices made thousands of years ago were not just aesthetically pleasing, they were functionally brilliant. The slight curvature of the Parthenon's base, a feature known as intosses, along with the subtle inclination of its columns inward, were long thought to be optical refinements to make the building look perfectly straight to the human eye. But FEA shows they do much more. These subtle curves actually help distribute seismic energy more evenly throughout the structure, preventing stress from concentrating at a single weak point and causing a catastrophic failure. The ancients, it seems, engineered their buildings to dance with the Earth's movements, and we now have the computer models to prove it. This same analytical power is being applied to Roman aqueducts, those iconic lines of arches marching across the European landscape. We marvel at their length, but the real engineering miracle is in their endurance. How can such a slender-looking structure support the immense weight and constant pressure of a flowing river channeled along its top? Finite element analysis allows engineers to create a virtual cross-section of a single arch and its supporting piers. They can then apply the massive downward force of the water-filled conduit, combined with the lateral forces of wind and the inevitable settling of the ground over time. The simulations show that the Romans had an almost intuitive understanding of load paths. The semicircular arch is a masterpiece of efficiency, channeling the tremendous weight above it down into the sturdy piers on either side, primarily putting the stone blocks into compression, a force that stone handles exceptionally well. The true stability, however, comes from the system. The analysis reveals that the sequential arrangement of identical arches creates a mutually supportive network. If one pier settles slightly, the loads are dynamically redistributed to the adjacent arches, preventing a progressive collapse. The Romans didn't just build a series of arches, they built a single, unified, and resilient structural organism. The simulations can even pinpoint the specific benefits of the Roman concrete used in the foundations and the pozzolana mortar, showing how its slight flexibility compared to modern rigid materials actually allowed the structure to accommodate small movements without cracking. This process of digital reverse engineering is doing more than just validating ancient brilliance. It is actively educating modern engineering. The principles uncovered in these virtual tests are inspiring new, sustainable designs. The seismic resilience of ancient structures, confirmed by FEA, is directly influencing the development of base isolation systems in modern skyscrapers and bridges. The way Inca polygonal masonry allows for movement is inspiring new types of flexible, dry stack retaining walls for use in earthquake zones. The Roman understanding of fluid dynamics in their aqueducts and water systems is informing more efficient designs for modern canals and spillways. By studying the past with our most advanced tools, we are not simply admiring history, we are mining it for actionable intelligence. The ancient world is becoming a vast, open-source library of proven engineering solutions, each structure a chapter written in stone, waiting for us to learn its lessons. This dialogue between the past and the present is proving that the most sustainable path forward may be to look backward, to a time when building for millennia was the only standard that mattered. There is a growing and urgent realization in the world of modern engineering and architecture that we have been building for the wrong timeline. Our current paradigm, focused on speed, cost efficiency, and often planned obsolescence, has created a landscape of infrastructure with an expiration date, a stark contrast to the ancient philosophy of building for millennia. As we face the escalating challenges of climate change and resource scarcity, the silent stones of the past are beginning to speak with a new and powerful urgency, offering a blueprint for a more resilient and sustainable future. The lessons are not about replicating their exact methods, but about embracing their core principles, a deep respect for local materials, an intuitive understanding of natural systems, and an unwavering commitment to longevity. Consider the starkest comparison, the concrete that surrounds us today versus the concrete that built Rome. Modern Portland cement, the backbone of contemporary construction, has a lifespan often measured in decades, especially in harsh marine environments where it cracks and crumbles as reinforcing steel rusts from within. We build, we repair, we replace in a constant, resource-intensive cycle. Now, look at the Roman breakwater at Caesarea, submerged and pounded by Mediterranean waves for 2,000 years. It hasn't just survived, it has grown stronger. The secret, as we've discovered, was a geopolymer recipe that used seawater as a catalyst for self-healing chemical reactions. The modern implications are staggering. Imagine a future where our seawalls, our bridges, our foundations are designed not to deteriorate but to improve with age. Scientists are now actively working to reverse engineer this ancient formula, not for historical curiosity, but to create a new generation of carbon-neutral cements that could dramatically reduce the environmental toll of our built environment. The Roman approach was fundamentally sustainable. They viewed durability as the ultimate form of efficiency, a principle we are desperately needing to relearn. This ancient wisdom extends far beyond the chemistry of materials and into the very physics of comfort. Long before the invention of air conditioning or central heating, ancient builders designed structures that maintained stable, comfortable temperatures using nothing but intelligent design and the thermal mass of the earth itself. Walk into a traditional adobe dwelling in the American Southwest or a stone-built cottage in the Mediterranean, and you'll feel it immediately. The thick, earthen walls act as a thermal battery. During the heat of the day, the walls absorb warmth, keeping the interior cool. At night, as the air temperature drops, the walls slowly release that stored heat, preventing the interior from becoming too cold. This is passive climate control, a system that requires zero energy to operate beyond the initial sun that shines on it. Modern architecture, with its reliance on glass and thin, lightweight materials, is the exact opposite. It heats up and cools down rapidly, creating a dependency on massive energy-consuming systems to maintain habitability. A forward-thinking movement in contemporary architecture, often called passive house design, is directly inspired by this ancient principle. Architects are now specifying massive, thermally active materials like rammed earth, thick stone, and specialized concrete to create buildings that need a fraction of the energy for heating and cooling, dramatically reducing their carbon footprint over a lifetime of use. The foundation in this context isn't just a base, it becomes an integral part of the building's environmental control system. This philosophy of biomimicry, of looking to nature and ancient adaptations for solutions goes even deeper. One of the most inspiring examples isn't from a human city, but from a termite mound. In the scorching deserts of Africa, termites construct towering earthen structures that maintain a remarkably constant internal temperature and humidity, despite wild swings in the external environment. They achieve this through a brilliant passive ventilation system. The mounds are built with a complex network of internal channels and vents, THAT, Chinese letter, Chinese letter, Chinese letter, Chinese letter, Chinese letter, Chinese letter, Chinese letter. As hot air rises and escapes through the top, it draws cooler air from the base, creating a constant, energy-free circulation. Architects and engineers are now studying these natural foundations to design buildings that breathe. The Eastgate Center in Harare, Zimbabwe, is a famous example. Instead of relying on conventional air conditioning, the building was designed to mimic the termite mound's ventilation, using a combination of thermal mass and carefully engineered airflows to regulate its temperature. The result is a massive office complex that uses less than 10% of the energy of a comparable conventionally cooled building. This is not primitive technology. It is sophisticated bio-inspired engineering, and it demonstrates that the most advanced solution is often one that has been tested and refined by nature, and occasionally by ancient humans for thousands of years. Ultimately, the most profound lesson from antiquity is a shift in perspective, from seeing the environment as an obstacle to be conquered to viewing it as a partner to be understood. The Incas at Machu Picchu didn't fight the mountain. They partnered with it, carving terraces that stabilized the slopes and designing foundations that became one with the bedrock. The Aztecs at Tenochtitlan didn't drain the lake. They learned to build upon it, creating a symbiotic relationship between their city and the water. This stands in direct opposition to much of modern development, which often involves bulldozing the land into a flat, featureless plain and then imposing a design from the outside. The ancient way was one of hyperlocality. They used the materials that were immediately at hand, the local stone, the local clay, the local timber. This eliminated the colossal carbon footprint of transporting materials across the globe. More importantly, these materials were already in equilibrium with the local climate. A granite block in the Andes knows how to handle the high-altitude sun and freezing nights. An adobe brick in the desert knows how to manage the extreme diurnal temperature swing. By using local materials, ancient builders automatically created structures that were inherently adapted to their environment. The modern push towards sustainable architecture is a return to this principle, emphasizing locally sourced, natural, and low-embodied energy materials. It's a recognition that true sustainability is not a one-size-fits-all technological fix, but a deeply contextual practice, a dialogue with the specific piece of earth upon which we build. The ancient goal was permanence, not just of the structure, but of the harmonious relationship between the building and its world. By looking back to these secrets beneath the stones, we are not retreating into the past. We are recovering a wisdom that is essential for building a truly enduring future. Yet, after all this talk of engineering principles and material science, we are left with a feeling that goes far deeper than intellectual curiosity. The true power of these places doesn't just lie in the technical brilliance we can analyze. It lives in the quiet, overwhelming emotion that washes over you when you stand amidst their ruins. It's a sensation that is both universal and deeply personal, a complex mix of awe, melancholy, and a strange, profound connection that transcends the centuries. We can study the how, but the why we are so drawn to these broken stones is a mystery as compelling as any engineering enigma. It's the emotional power of ruins, a force that has inspired poets, artists, and explorers for generations, and it begins with a simple, humbling realization: the sheer scale of deep time. When you walk through the empty streets of Pompeii or touch the sun-warmed stones of a Maya pyramid, you are not just looking at an old building, you are standing at the edge of a vast chasm of time. You are confronted with the literal groundwork of people who laughed, loved, worried, and dreamed thousands of years before you were born. This isn't an abstract historical date, it's a visceral feeling. You see the ruts worn into the stone pavement by ancient chariot wheels. You stand in a kitchen where meals were prepared. You see the graffiti scratched onto a wall by a long-vanished hand. These are not monuments to abstract gods or faceless kings. They are the remnants of everyday life, frozen in a moment of catastrophe or simply worn away by the slow, patient hand of time. This perspective is profoundly humbling. It shrinks our own brief lifespans and modern preoccupations down to a manageable size, reminding us that we are merely the latest visitors in a story that began millennia ago and will continue long after we are gone. It's a gentle, powerful lesson in what truly endures. This feeling is closely tied to what philosophers and psychologists sometimes call the sublime, the strange beauty we find in things that are vast, powerful, and even terrifying. There is an undeniable, haunting beauty in decay itself. The way morning light filters through a collapsed archway at a Roman villa, or how vibrant green moss softens the sharp edges of a granite block at an Inca site, creates a scene more poignant than any perfectly preserved museum piece ever could. This beauty isn't about perfection, it's about the poetry of impermanence. It's the sight of a tree slowly, inexorably, splitting apart a massive wall with its roots, a vivid demonstration that nature always, eventually, reclaims what we build. This interplay between human creation and natural reclamation is a powerful narrative in itself. It speaks to a cycle of growth and decay, of ambition and entropy that feels fundamentally true. We are moved by the stubborn persistence of the stones, but also by the gentle, inevitable victory of the vines and the weather. This haunting quality sparks our imagination in a way a complete building cannot. An intact structure tells you a finished story. A ruin, however, invites you to become the author. Your mind instinctively tries to fill in the gaps. You look at a crumbling foundation, and you imagine the walls that once rose from it, the roof that offered shelter, the lives that unfolded within those spaces. You become an active participant in reconstructing the past, collaborating with the stones to envision the world they were part of. This act of imagination is a powerful form of time travel, a deeply personal connection that makes the past feel immediate and alive. This emotional resonance is not just a passive experience, it is the very engine that drives the modern phenomenon of heritage tourism. Millions of people each year travel across the world not to relax on a beach, but to seek out this specific feeling, to stand in the shadow of Machu Picchu, to walk the Via Appia, to gaze at the Great Pyramid. They are chasing that humbling perspective, that connection to deep history. This collective desire, this emotional pull, is what funds the ongoing work of archaeology and preservation. The donations to historical societies, the entrance fees to national parks, the public support for protecting these sites from development or looting, all of it is fueled by this profound human need to connect with our shared past. We intuitively understand that these places are irreplaceable libraries, not just of engineering knowledge, but of human experience. They are a tangible link to our collective story, and we feel a responsibility to protect them for future generations to experience that same awe. This connection ultimately brings us back to the most important truth of all, that these were not projects built by abstract forces or mythical giants. Every perfectly cut stone, every strategically placed drain, every astronomically aligned foundation was conceived, planned, and placed by a human being. Someone whose name is lost to history stood on that very spot and made a decision. They felt the heat of the sun on their back, they wiped sweat from their brow, they felt pride in their work, and they probably wondered, just as we do today, about their place in the world and the legacy they would leave behind. This realization bridges the gap of millennia. It transforms the ruins from cold, silent stones into a message. They are a testament to human ambition, ingenuity, and the universal desire to create something that outlasts a single lifetime. And it is this very human connection that makes us so eager to learn about the modern individuals who heard that message and dedicated their own lives to ensuring it would be heard by the world. Behind every great ruin, there is a great story of discovery, a human drama of obsession, perseverance, and often sheer luck. The silent stones we marvel at today did not simply reveal themselves. They were coaxed into the light by individuals whose passion and dedication bridged the chasm of centuries. These archaeologists and theorists are the essential translators, the ones who turned scattered rubble and enigmatic foundations into a coherent narrative of ancient genius. Their stories are not just footnotes in history, they are epic tales of exploration that add a thrilling layer of adventure to the science of the past. Consider the now iconic image of Machu Picchu, its terraces seeming to float among the Andean clouds. That vision was introduced to the world largely through the efforts of Hiram Bingham, an American academic and explorer who, in 1911, was led up the treacherous mountainside by local Quechua farmers who had always known of the city's existence. Bingham's story is a classic adventure tale fueled by a quest for the last capital of the Incas. When he first laid eyes on the site, it was shrouded in dense vegetation, with vines and trees weaving through the stonework. What set Bingham apart was not just his discovery, but his relentless drive to document and publicize it. He returned with expeditions funded by Yale University and the National Geographic Society to clear and photograph the city. His articles and lectures captured the global imagination, transforming Machu Picchu from a local secret into a world wonder. Yet his legacy is complex. While he brought international attention and preservation efforts, his methods of removing artifacts to be studied abroad are now viewed critically, raising important questions about cultural heritage and the ethics of early 20th century archaeology. Bingham's story reminds us that discovery is rarely a simple, heroic narrative. It is often intertwined with the cultural and political currents of its time. While some discoveries happen in the field, others unfold in the quiet realm of study and theory, challenging ideas that have stood for centuries. For generations, the construction of the Great Pyramid of Giza was explained by one dominant idea: a massive, straight ramp built up one side, growing ever longer and more immense as the pyramid rose. But this theory had serious flaws, not least the staggering volume of the ramp itself, which would have rivaled the pyramid in the amount of material required. Then came Jean-Pierre Houdin, a French architect who approached the mystery not as an archaeologist but as a builder. He spent years studying the problem, and in the early 2000s he proposed a radical new theory, an internal spiral ramp. Houdin suggested that the Egyptians used a straight ramp only for the bottom third of the pyramid to haul the largest blocks. For the upper two-thirds, he hypothesized that the builders constructed a corkscrewing ramp inside the pyramid structure, tunneling upward just behind the outer casing stones. This would have been far more efficient, requiring a fraction of the material, but Houdin faced a wall of skepticism from the academic establishment. His breakthrough came from an unexpected partnership with a microgravity specialist and later from thermal imaging scans that seemed to reveal less dense areas within the pyramid empty spaces that aligned perfectly with the path of his proposed internal ramp. Houdin's story is a testament to the power of an outsider's perspective and the painstaking work of validating a controversial idea against the weight of conventional wisdom. It shows that the secrets beneath the stones are still being decoded, not just with shovels, but with software, scanners, and a fresh pair of eyes. If Bingham was the swashbuckling adventurer and Howden the innovative theorist, then Dame Kathleen Kenyon represents the meticulous, methodical scientist who revolutionized the very process of excavation. In the mid-20th century, archaeology was still emerging from an era often focused on finding treasures and grand monuments. Kenyon, working at the ancient mound of Jericho in the 1950s, introduced a level of precision that would become the gold standard. Her technique was the Wheeler-Kenyon method, named for her mentor and refined by her. It involved digging in small, carefully measured squares, separated by unexcavated blocks of earth. This allowed for a perfectly preserved vertical record of the layers or strata, like reading the pages of a history book stacked one on top of the other. By meticulously analyzing the color, composition, and artifacts within each layer, Kenyon could construct an incredibly detailed timeline of occupation. Her work at Jericho did not just uncover buildings, it peeled back the city's history layer by layer, revealing that it was one of the world's oldest continuously inhabited settlements, with foundational remains dating back thousands of years before the pyramids were even a concept. It was Kenyon who uncovered the famous stone tower of Jericho, a monumental structure from the pre-pottery Neolithic period that forced a complete re-evaluation of the capabilities of the world's first town dwellers. Her legacy is not a single spectacular find, but a rigorous methodology that taught the world to dig slowly and read the earth carefully, ensuring that the context of a discovery, the story of how and when it was laid down, is preserved as carefully as the object itself. These pioneers, in their vastly different ways, shared a common trait, an unwavering curiosity that propelled them past obstacles and skepticism. They remind us that our understanding of the ancient world is not a static collection of facts, but a living, evolving conversation, one that is continually enriched by the dedication of those who listen closely to the whispers from the past. For all the brilliant solutions we have uncovered and the ancient principles we have successfully decoded, there remains a collection of foundational puzzles so stubborn, so perplexing, that they continue to defy even our most advanced explanations. These are not mere gaps in our knowledge, they are gaping chasms that challenge the very boundaries of what we believe was possible. They stand as silent, monumental questions, ensuring that the study of ancient engineering remains a living, breathing, and wonderfully contentious field, a frontier where a single new discovery could still rewrite entire chapters of human history. Let's journey to three of the most baffling sites on Earth, starting with a place where the stones are so colossal they seem to belong to the realm of giants. In the Bekaa Valley of Lebanon lies the sprawling Roman temple complex of Baalbek, a site of undeniable grandeur. But it is not the well-known Roman columns that cause the greatest head-scratching, it is the foundation upon which they were built. On a massive terrace known as the Trilithon, we find 3 limestone blocks, each weighing an estimated 800 tons. That is the weight of 2 fully loaded jumbo jets. And just a stone's throw away in a quarry lies an even larger monolith nicknamed the Stone of the Pregnant Woman, weighing a staggering 1,000 tons. The sheer scale is incomprehensible. How were these blocks quarried? How were they moved over a kilometer from the quarry to the site? And most mysteriously, how were they lifted and positioned with such precision onto a foundation wall that stands nearly 20 feet tall? The Romans, master engineers though they were, left no records of the methods used for this specific task. The conventional explanation of rollers, levers, and immense human labor begins to strain under the weight of such mass. The precision with which these blocks are fitted together is also extraordinary, leaving barely a hair's breadth between them. The entire construction sequence for this foundation remains one of the world's greatest logistical mysteries, a problem of physics and manpower that we have yet to solve to anyone's complete satisfaction. From the sun-drenched valleys of Lebanon, we travel to the deep, blue waters off the coast of Japan's Yonaguni Island. Here, beneath the waves, lies a formation that has sparked a fierce debate since its discovery in the 1980s. The Yonaguni Monument is a massive sandstone structure covered in what appear to be perfectly straight terraces, sharp right angles, and stair-step patterns that climb its sides. To some researchers, these features are unmistakably artificial. They point to what looks like a carved archway, a processional roadway, and even a star-shaped platform, arguing that the geometry is too perfect and repetitive to be the work of natural erosion alone. If they are correct, this would be the foundation of a structure dating back over 10,000 years, from a time when sea levels were much lower, and this area was dry land, a discovery that would fundamentally alter our understanding of prehistoric human civilization in the Pacific. However, other geologists offer a compelling counter-argument. They explain that the sandstone in this region is naturally fractured along horizontal and vertical planes. The powerful underwater currents of the area, they suggest, could have selectively eroded the softer rock along these natural joints, creating the remarkably geometric features we see today, all through entirely natural processes. The debate is a perfect storm of ambiguity. The site lacks the definitive proof that would settle the argument, such as clearly human-made artifacts like tools or carvings found in situ. So we are left with a haunting question. Are we looking at the sunken foundations of a lost, ancient city, a monument to a culture whose name we don't even know, or are we simply witnessing the incredible artistic power of nature, which can sometimes create forms that perfectly mimic human design? The Yonaguni Monument remains an enigma wrapped in ocean currents, a beautiful and tantalizing puzzle on the seafloor. Then there is the haunting mystery of Easter Island, known locally as Rapa Nui. The island is famous for its nearly 900 massive stone figures, the moai, their stern faces gazing inland. For a long time, the biggest question was how these multi-ton statues were transported miles from the quarry where they were carved. Various theories involving log rollers, rocking motions, and even a walking method using ropes have been proposed and even demonstrated on a small scale. But in recent years, an even more perplexing mystery has come to the forefront. How were the moai crowned with their massive, cylindrical topknots, known as pukao? These red scoria stone hats, some weighing over 10 tons, were quarried from a different part of the island. The challenge was not just moving them, but lifting them onto the heads of statues that were already standing on tall, ceremonial platforms called ahu, some of which reached heights of 15 feet or more. Prevailing theory suggests the use of a long, gradual ramp made of stones and earth. The pukao would have been dragged up this ramp and then somehow maneuvered into place on top of the moai. But this is an incredibly precarious operation, requiring immense precision to avoid toppling the statue itself. Another, more ingenious theory proposes that the pukao were actually placed on the heads of the moai before they were erected. The statue would be laid face down on the ground, the pukao rolled into position on its head, and then the entire assembly would be raised upright onto the ahu platform. This method seems mechanically more feasible, but it also presents its own set of complex challenges in raising such a top-heavy combination. The truth is, we still don't know for certain. The method remains a subject of lively debate among archaeologists, a testament to the fact that even on one of the most isolated islands on Earth, the ingenuity of its ancient inhabitants continues to outsmart our modern attempts at a definitive explanation. These enduring enigmas, the impossible weight of Baalbek, the ambiguous geometry of Yonaguni, and the precarious hat trick of Easter Island serve a vital purpose. They are humbling reminders that for all our satellite imagery and computer models, the ancient world has not yet yielded all its secrets. They force us to keep questioning, to remain open to new ideas, and to acknowledge that the past may hold surprises that challenge our most deeply held assumptions. Each unanswered question is an invitation, a challenge flung across the centuries, urging us to look closer, think deeper, and continue the global endeavor of uncovering the secrets that still lie buried, waiting for their story to be told. When we step back and look at the entire ancient world, a remarkable pattern begins to emerge. It's a pattern that suggests a kind of universal architectural language, one spoken not in words but in stone and earth. Across vast oceans and impassable mountain ranges, cultures that had absolutely no contact with one another repeatedly arrived at the same brilliant solutions to the fundamental challenges of building. This wasn't a case of shared blueprints or secret communication. It was the result of different minds confronting the same immutable laws of physics and arriving at logically similar conclusions. This phenomenon, known as convergent evolution in biology, has a powerful parallel in the story of human engineering. It tells us that the principles of stable foundations are not cultural inventions, but fundamental truths waiting to be discovered by any society with the ambition to build for the ages. One of the most striking examples of this global conversation in stone is the corbel arch. Travel to the citadel of Mycenae in Greece, and you will walk through the famous Lion Gate. Above the massive stone lintel, a triangular space is filled with a sculpted relief, but the true engineering marvel is the gate itself, and even more so, the hidden treasure known as the Treasury of Atreus. This magnificent Tholos tomb features a long, corbelled passageway. The technique is simple in concept yet profound in its execution. Instead of using a true arch with a central keystone, the Mycenaean builders stacked horizontal courses of stone, each one projecting slightly inward over the one below. Layer by layer, the walls gradually leaned in until they met at the top, creating a sturdy, beehive-like dome. This method effectively channels the immense weight of the earth above downward through the walls, creating a stable, self-supporting structure that has stood for over 3,000 years. Now take a leap across the Atlantic Ocean and several centuries forward in time. In the lush jungles of the Yucatan Peninsula, the Maya were constructing their own grand buildings like the palace at Palenque. And there, in the dark, humid corridors of that ancient city, you find the exact same architectural solution, the corbel arch. The Maya version is often called a false arch, and it has an even more pronounced inward incline, creating a narrow, triangular-shaped vault. The similarities are uncanny. Two cultures separated by an ocean and a millennium both discovered that by gradually stepping stones inward, they could create a strong, enclosed space without the risk of collapse. They were both solving the universal problem of how to span a gap and support a roof, and gravity led them to the same elegant answer. This pattern of parallel invention becomes even more dramatic when we look at the most iconic symbols of ancient ambition, the massive raised platforms. In the fertile plains between the Tigris and Euphrates rivers, the Sumerians and their successors built ziggurats. These were not tombs but sacred mountains, towering stairways for the gods to descend to earth and for priests to ascend closer to the heavens. The ziggurat was essentially a series of stacked, rectangular platforms, each level smaller than the one below, creating a stepped pyramid shape. The core was typically made of sun-dried mud brick, a readily available but vulnerable material. To protect this core from the elements, especially the destructive force of rain, the builders faced the entire structure with a skin of fired, waterproof bricks. This was foundational engineering on a grand scale, a deliberate design to create a permanent, elevated sacred space on a flat plain. Now look across the world to the coast of Egypt. The step pyramid of Djoser at Saqqara is arguably the first colossal stone building in history, and its form, a series of stacked rectangular platforms, each level smaller than the one below. While its purpose as a tomb was different from the ziggurate's temple function, the engineering principle was virtually identical. The stepped structure is inherently stable, distributing weight efficiently and preventing the slumping that would threaten a smooth-sided mound. This same form appears again independently in the stepped pyramids of Mesoamerica, like the Temple of the Inscriptions at Palenque. The convergence is undeniable. Whether using mud brick in Mesopotamia or limestone in Egypt, builders from these isolated cultures understood that the pyramidal form was the most effective way to achieve great height while ensuring foundational stability. They were all mastering the law of gravity, discovering that a wide base and a narrowing profile was the key to reaching for the sky without falling back to Earth. What does this global chorus of similar solutions truly mean? It points to a profound idea that effective foundational engineering is less about cultural secrets and more about a shared, intuitive grasp of physics. Gravity acts the same way in Mexico as it does in Mesopotamia. Seismic energy travels through the ground in Peru in the same way it does in Pakistan. When intelligent human beings set out to solve the problem of creating something permanent, they are all playing by the same natural rules. The Incas needed their walls to flex during earthquakes, so they developed polygonal masonry. The Romans needed their concrete to withstand seawater, so they developed a pozzolanic recipe. These are unique innovations, specific responses to local challenges. But the underlying principles, energy dissipation, material durability, are universal. The convergent evolution we see in arches and pyramids suggests that there are only so many stable ways to arrange mass against the pull of gravity. Intelligent builders, through observation, trial, and error, will inevitably circle in on these optimal forms. This global perspective does more than just highlight similarities. It deepens our respect for the universal human drive to create a legacy. From the deserts of Egypt to the jungles of Central America, from the mountains of Peru to the plains of Iraq, humanity demonstrated a common yearning to imprint itself upon the landscape, to build structures that would whisper their stories to the future. This wasn't a competition, it was a collective, unconscious project of our species, a testament to the fact that the desire to build something that lasts is woven into the very fabric of human ambition. But for the ancient mind, the foundation was never just a matter of physics and materials. After the surveyors had mapped the stars and the engineers had tested the soil, there came a moment of profound significance, a ceremony that transformed the construction site from a mere location into a sacred center. The laying of the foundation was as much a ritual act as a technical one, a crucial step in weaving the physical structure into the invisible fabric of the spiritual world. This symbolic dimension was not a secondary concern. It was essential to the building's ultimate purpose, its legitimacy, and its perceived durability. Across the globe, cultures developed elaborate rituals to ensure that their creations were not just physically sound, but also divinely sanctioned. In Mesopotamia, the cradle of urban civilization, this practice took a remarkably concrete form. Before a single brick was laid for a temple or a palace, the builders would carefully deposit a foundation box, often made of baked clay or metal, into a specially prepared pit in the ground. Inside this box, they placed a collection of objects charged with meaning, small, carefully crafted figurines of gods or protective deities, and perhaps most importantly, inscribed tablets. These tablets were not mere records, they were direct messages to the gods. They detailed the name of the ruler who commissioned the building, the gods to whom it was dedicated, and a series of prayers and curses. The prayers asked for divine protection and longevity for the structure, while the curses were directed at any future king or person who might dare to damage or deface the building, calling upon the gods to unleash terrible punishments upon them. These deposits were a form of spiritual insurance. By physically embedding these invocations within the very bones of the building, the Mesopotamians believed they were creating a permanent covenant with the divine, ensuring that the structure would stand under the watchful eyes of the gods for all eternity. It was an act of immense consequence, meant to secure a legacy that would outlast empires. This concept of aligning human construction with cosmic order finds one of its most sophisticated and enduring expressions in the Chinese tradition of Feng Shui, which translates literally as wind and water. Far from being a simple superstition or a modern decorating trend, classical Feng Shui was a complex system of geomancy, a science of placement that governed the location, orientation, and layout of everything from a humble home to an imperial capital. The foundational principles of Feng Shui were based on a deep observation of the natural landscape and a desire to harness the flow of vital energy, or Qi, for the benefit of the inhabitants. A Feng Shui master, before any digging began, would spend days analyzing the site. He would look for the dragon veins, the subtle energy lines believed to run through the earth, often corresponding to mountain ranges and ridges. The ideal building site was often described as an armchair position, protected by hills or higher ground at the rear, embraced by lower arm hills on the sides, and open to a vista at the front, preferably with a meandering stream or river to bring nourishing Qi. The orientation was critical, meticulously calculated using a luopan, a complex compass ringed with cosmological symbols, to align the structure harmoniously with the magnetic fields of the Earth and the symbolic animals of the Chinese zodiac. To build without this careful consideration was to risk creating a structure that was spiritually inert or, worse, attracted negative, stagnant energy that could lead to misfortune, illness, or financial ruin for those who lived within. The foundation, therefore, was not just a physical base. It was the anchor point for a beneficial relationship between the human world and the dynamic forces of the natural and cosmic environment. A city like ancient Beijing was laid out according to these principles, its walls and major avenues aligned to create a harmonious flow of energy, demonstrating that the foundation of an entire civilization could be conceived as a single, grand act of symbolic placement. Underlying all of these diverse rituals was a powerful, unifying idea, the foundation stone as an axis mundi, a world navel. This was the belief that the chosen site was the central point of connection between the earthly realm and the divine, the place where heaven and earth met. By laying the foundation, the builders were effectively establishing a portal, a fixed point of contact with the gods. This concept is vividly illustrated in the traditions surrounding the foundation of the Jewish temple in Jerusalem. The stone upon which the altar was built was known as the Even Shetia, the foundation stone. Jewish tradition held that this was the very stone from which the creation of the world began, and it was from this point that the world expanded into its present form. It was considered the spiritual center of the world, the point of first contact between God and creation. Similarly, in ancient Rome, before a new city was founded, a priest would ritually mark its center by digging a small pit known as the mundus. Into this pit, the first citizens would throw offerings, a handful of earth from their original homeland, along with fruits and other symbols of fertility. This pit was then covered with a stone, and it became the symbolic and religious heart of the city. the point from which all distances were measured and the conduit through which the citizens could communicate with the gods of the underworld. In both cases, the foundation ritual was an act of cosmic replication. It was an attempt to recreate the order of the universe on a human scale, to build a microcosm that reflected the harmony of the macrocosm. The stability of the building was thus inextricably linked to its symbolic alignment with the cosmic order. If the foundation was spiritually sound, connected to the divine, then the structure itself would partake in that eternal stability. These rituals served a crucial social function as well. A massive construction project requiring the labor and resources of an entire community needed more than just technical justification. It needed ideological legitimacy. The elaborate foundation ceremony, often presided over by the king or high priest, was a public spectacle that reinforced the social order. It demonstrated that the ruler had the favor of the gods and the authority to command such an ambitious undertaking. When people saw their leader depositing precious objects into the foundation or performing sacred rites, it transformed the project from a burdensome tax on their labor into a shared religious duty, a collective act of piety that would bring prosperity and protection to the entire community. The foundation became a symbol of communal identity and divine favor. To question the project was to question the gods themselves. This symbolic layer was as vital to the longevity of the structure as the quality of the mortar. A building that was revered as sacred, that was believed to be under divine protection, was far more likely to be maintained, repaired, and respected by future generations. It was protected not just by its physical strength, but by a taboo, a cultural memory of its spiritual significance. The stones themselves might endure for centuries, but it was the meaning embedded in them by these powerful rituals that truly granted them a permanence in the human heart and mind, ensuring that their story would be told long after the last builder had passed away. While we can analyze the stones themselves to understand the physics of their placement and use technology to map their vast arrangements, there is nothing quite like hearing a story directly from the person who lived it. In a remarkable twist of fate, we sometimes can, scratched into the very surfaces of these ancient foundations, carved onto dedicated plaques and preserved in buried caches, the ancient builders left behind messages. These are not grand boasts intended for public monuments, but the practical, often personal, notes of the project managers, engineers, and laborers themselves. They are the memos, the time cards, and the cornerstones of history, offering us a direct, unfiltered line to the minds behind the megaliths. Perhaps the most human of these messages are the simple quarry marks found on the stones of the Great Pyramid. If you look closely at some of the massive limestone blocks, especially those in the relieving chambers above the king's chamber, you can see marks painted in red ochre. These are not random graffiti, they are administrative shorthand. They often appear as hieroglyphic signs that spell out the names of work gangs, and these names are wonderfully revealing. We find groups with proud, patriotic titles like the Vigorous Gang or the Enduring Gang, suggesting a sense of camaraderie and esprit de corps. But we also find names that feel surprisingly personal and even affectionate, such as the Drunkards of Menkara or the Friends of Khufu. These inscriptions completely upend the old Hollywood image of a brutal, slave-driven operation. They paint a picture of a highly organized workforce, divided into teams that took on unique identities, almost like modern-day corporate divisions or sports teams. These marks were essential for logistics, allowing overseers to track which team was responsible for quarrying and delivering which block, ensuring accountability in a project of unimaginable complexity. They are a powerful reminder that these stones were not moved by an anonymous mass, but by named groups of individuals who likely took pride in their contribution to a project that would define their civilization for eternity. Moving from the personal to the profoundly official, we travel to ancient Mesopotamia, where the act of laying a foundation was a sacred covenant, recorded for both the gods and posterity. Kings like Gudea of Lagash or Nebuchadnezzar II of Babylon practiced a ritual that has given archaeologists one of their greatest treasures, the foundation deposit. Before a temple or a palace was built, a small box or capsule, often made of clay or precious metal, would be buried in the foundation trench. Inside, they placed a variety of objects, but most importantly, they included inscribed tablets. These were not mere records of construction, they were legal and divine contracts. Written in the meticulous wedge-shaped script of cuneiform, these tablets detailed everything. They named the ruler who commissioned the building, the specific deity to whom it was dedicated, and provided a precise account of the construction process itself, the materials used, the dimensions of the structure, and the timeline of its creation. But these texts went beyond simple facts. They were filled with prayers, asking the gods to grant the building eternal stability and to bestow a long reign upon the king. And then came the curses. These were vivid, terrifying invocations aimed at any future ruler who might damage, deface, or claim the building as their own. A typical curse might read something like, "May the god Enlil tear out his foundations and destroy his progeny." This practice was a form of spiritual insurance, an attempt to protect the king's legacy through divine intimidation. For modern historians, these foundation cylinders are priceless. They provide an exact date for the structure, a wealth of information about the materials and methods used, and a deep insight into the political and religious ideology of the time. They are the ultimate primary source, a cornerstone of historical fact buried literally within the cornerstone of the building. This practice of inscribing the very fabric of a structure was a global phenomenon. In the Roman Empire, builders frequently stamped bricks and tiles with the mark of the manufacturer, the brickyard owner, and even the consuls for that year, providing a precise date that allows archaeologists to piece together the growth phases of a city with remarkable accuracy. In ancient China, foundation stones for important buildings might be inscribed with characters detailing the purpose of the structure and the date of its construction according to the imperial calendar. Even the Viking runestones of Scandinavia, while often standing above ground as memorials, served a similar function, to permanently etch a name, a deed, or a claim to the land into a substance that would outlast memory. What unites all these traditions is a universal human desire to speak to the future, to assert we were here, this is what we built, and this is what it meant to us. The medium was the message, and the message was permanence. The true power of these inscriptions, however, lies in their ability to separate romantic speculation from archaeological fact. For centuries, the construction of Stonehenge was shrouded in myth and mystery, attributed to druids, giants, or even the wizard Merlin. Then, in the 1950s, a chance discovery changed everything. A set of carvings was identified on several of the massive sarsen stones, intricate depictions of Bronze Age axe heads and a single, distinctive dagger. This was not random graffiti. It was a specific artistic style known from the Mycenaean civilization of ancient Greece, dating to around 1600 BC. This single piece of evidence, carved directly into the stone, provided a crucial anchor point. It suggested that the people who erected the final phase of Stonehenge were part of a wider European culture, connected to the sophisticated societies of the Mediterranean. It didn't tell us how they moved the stones, but it told us when and gave us a vital clue about who. It moved the discussion from the realm of pure mystery into the realm of datable cultural history. Similarly, the intricate carvings and hieroglyphic texts on the walls of Mayan temples and pyramids do more than just tell stories of gods and kings. They provide dynastic sequences, record exact dates using the sophisticated long count calendar, and describe specific historical events, including wars, alliances, and the dedication of the very buildings they adorn. They are the history books of the Maya, written in stone by the people who lived that history. Piecing together these scattered messages, the quarry mark in Egypt, the foundation tablet in Mesopotamia, the axe carving in England allows us to assemble a new, far more dynamic picture of the ancient world. We move from seeing static ruins to understanding living, breathing projects. We can almost hear the foreman shouting instructions to the vigorous gang, see the Mesopotamian priest carefully placing the foundation box in the trench, and sense the Mycenaean artist carefully etching his familiar symbol onto the alien stone of Salisbury Plain. These inscriptions give voice to the anonymous. They restore the humanity to what can otherwise seem like superhuman achievements. They remind us that these were not acts of magic or alien intervention, but the culmination of human intelligence, organization, and sheer determination. They are the ultimate direct evidence, the personal signatures on the grand blueprints of history, ensuring that the names and efforts of the builders would, against all odds, endure as long as the stones they so masterfully placed. When we look at an ancient city, it's easy to see a collection of separate buildings, temples, houses, markets. But if we shift our perspective, something far more remarkable comes into focus. These great urban centers were not just assemblages of stone. They were living, breathing organisms, and their foundations were the very skeleton and circulatory system that gave them life. Just as our own bodies rely on a sturdy frame to stand upright and a network of veins and arteries to distribute nutrients, a city depended on its foundational infrastructure to manage its metabolism, the constant, vital flow of water, waste, energy, and people. The initial act of laying a foundation was not merely the start of construction. It was the moment of conception for a complex, evolving ecosystem, a deliberate plan that would dictate the health and longevity of the urban body for centuries to come. Think about the most basic needs of any living thing. It must drink, it must eat, and it must expel waste. An ancient city was no different. Its circulatory system was the hidden network of channels, pipes, and drains woven into its foundational layers. At Mohenjo-Daro in the Indus Valley, this system was so advanced that every single house was connected to a covered, city-wide drainage network. This wasn't an afterthought. It was part of the original blueprint laid down before the streets were paved. The foundation served as the main artery, with smaller clay pipes from individual homes acting like capillaries, all feeding into larger brick-lined conduits that ran beneath the streets. These drains were carefully sloped to ensure a constant flow, preventing blockages and stagnation, much like the peristaltic action of our own digestive tracts. The city literally consumed fresh water and expelled waste through this foundational system, a process essential for preventing disease and maintaining public health. This integrated approach meant that the foundation was not a passive slab. It was an active, managing entity. It governed the flow of the city's lifeblood, ensuring that the vital fluids of water and waste moved efficiently to keep the entire organism functioning smoothly. Just as a strong skeleton allows a body to grow tall and support its own weight, a stable foundational platform allowed a city to achieve density and verticality. The massive raised platforms of Mesopotamian ziggurats or the painstakingly leveled bedrock beneath the Great Pyramid did more than just provide a flat surface. They created a stable base upon which immense weight could be stacked, enabling the city to grow upward rather than just sprawling outward. This vertical growth, this urban density, is what allowed for the specialization and cultural complexity we associate with civilization. A stable foundation meant that multi-story buildings were possible, that grand temples could soar toward the heavens, and that populations could concentrate in a relatively small area. This density, in turn, fueled innovation, trade, and the exchange of ideas. The foundation was the unseen enabler of this urban concentration. Without the confidence that the ground would not shift or settle, this vertical ambition would have been impossible. The city's skeletal system gave it its form and its strength, allowing it to reach for the sky without collapsing under its own ambition. This systemic view reveals the incredible foresight of ancient urban planners. They did not see a water system, a road network, and building foundations as separate projects. They understood them as deeply interconnected components of a single, unified whole. The street grid itself was part of this foundational metabolism. In cities like Mohenjo-Daro, the streets were not flat. They were precisely graded to direct rainwater away from residential areas and into the main drains. The central plazas and courtyards were subtly angled to act as collection basins. This means the entire topography of the city was engineered to work in concert with its underground circulatory system. The flow of people along the streets and the flow of water beneath them were two aspects of the same life force. The foundation was the interface where these flows met and were managed. This holistic planning allowed the city to adapt and evolve. As new neighborhoods were added, they could be seamlessly tied into the existing metabolic network, much like a growing organism developing new limbs and vessels. The foundation was the genesis point for this adaptable, resilient system, a master plan that could accommodate growth and change without breaking down. When we view these ancient achievements through this lens of the city as a living organism, every engineering feat we've discussed suddenly clicks into place as part of a coherent, brilliant whole. The self-healing Roman concrete was not just a clever material. It was the immune system of a maritime city's foundations, repairing damage from a corrosive environment. The earthquake-resistant joints of Inca masonry were not just clever physics. They were the flexible ligaments that allowed the urban body to sway with seismic tremors without breaking its bones. The celestial alignments were not just spiritual gestures. They were the city's connection to the cosmic cycles that governed its agricultural and ritual life, its way of staying in rhythm with the universe. This systemic understanding is the ultimate key to appreciating the true genius of the ancient world. It wasn't about isolated tricks or lucky accidents. It was about a profound, integrated philosophy of design that saw human settlement as a dynamic partnership with the natural world. The foundation was the point where this partnership was sealed, a covenant written in stone and earth that said, "We will build here and we will build in harmony." This holistic legacy, written into the very ground of countless lost cities, challenges us to think differently about our own urban future, forcing us to confront the ultimate question of what we are building today and what story our own foundations will tell to those who come after us. And so, our journey through the secrets beneath the stones brings us to a final, profound realization. These ancient foundations are far more than just relics of the past. They are a living library of human ingenuity, a testament to a philosophy of building that we have, in many ways, forgotten. The narrative they reveal is not one of primitive struggle, but of breathtaking intelligence, resilience, and an ambition that thought not in years, but in millennia. From the self-healing geopolymer concrete of Roman harbors to the dancing, earthquake-resistant walls of the Incas, these masterpieces teach us a unifying lesson. True engineering mastery is not about conquering nature with brute force, but about working in harmony with it. It is about a deep, intuitive understanding of the fundamental laws of the physical world: gravity, hydrology, seismic energy, and using that knowledge to create structures that are not just strong, but symbiotic with their environment. This ancient wisdom stands in stark contrast to much of our modern approach. We live in an age of disposable construction, where buildings are often designed with a lifespan of decades, not centuries. We consume vast resources to create structures that fight their environment, requiring immense amounts of energy to heat and cool, and that often deteriorate rapidly, creating a cycle of constant repair and replacement. The ancient builders, by comparison, viewed their work as a covenant with the future. They planned for the long term, using local, durable materials and designing systems that leveraged natural forces for stability and comfort. Their goal was permanence, and in that goal, they achieved a level of sustainability that we are only now beginning to appreciate as essential. The passive climate control of thick adobe walls, the natural ventilation principles inspired by termite mounds, the use of materials that improve with age, these are not quaint historical footnotes. They are viable, powerful solutions to the pressing challenges of climate change and resource depletion that we face today. These ruins are active classrooms, and the lessons they offer on durability, energy efficiency, and environmental integration have never been more relevant. This legacy in stone challenges us to reconsider the very purpose of our own creations. Are we building burdens for future generations, mountains of waste and crumbling infrastructure that will need to be managed and replaced? Or can we, like the ancients, strive to create gifts for the future? The choice is ours. The principles are there, encoded in the bedrock of Machu Picchu, the swamps of Venice, and the deserts of Egypt. They remind us that our most brilliant innovations may not always lie in inventing something new, but in rediscovering a timeless wisdom that prioritizes longevity over expediency, harmony over domination, and legacy over short-term gain. The story does not end here. In fact, the most exciting chapter may be just beginning. Every new technological tool, from ground-penetrating radar to satellite imaging, is peeling back another layer of the Earth, revealing lost cities and hidden foundations that expand our understanding of the ancient world. The next great discovery is waiting, hidden just beneath the surface of a farmer's field, under the dense canopy of a jungle, or even submerged beneath the waves. It invites us to keep digging, both literally with our trowels and intellectually with our curiosity. Each stone turned over, each foundation mapped, adds another piece to the grand puzzle of human achievement. So the next time you walk past an old stone wall or gaze at a picture of a distant ruin, remember that you are not looking at a dead past. You are looking at a conversation that has been ongoing for thousands of years, a conversation about how to live wisely and build enduringly on this planet. The secrets beneath the stones are still speaking. The only question is, are we